to. Good. Okay, so we are done with today's July 10th, 2023. And we're going to start a new chapter. We finished with relativity. Finished with relativity, special relativity, right? And now what we're going to do, we're going to start a chapter on matter waves. The book called it matter waves, photons and matter waves. All right. Chapter 38. Photons and matter waves. A better title for this chapter would be Introduction to Quantum Mechanics. Introduction to Quantum Mechanics. Okay, or how the microscopic world functions, right? That's what quantum mechanics is all about. It's about how the microscopic world functions before quantum mechanics. Before quantum mechanics, we had thermodynamics. That was the theory that was behind the microscopic world. Quantum mechanics combined with electricity and magnetism. And that's what we call the classical theory. The theory before the 20th century. The theories before the 20th century. So special relativity is a 20th century theory. Is special relativity and quantum mechanics, right?
Hey, Professor.
Oh, I gotta share the screen, right? Thank you.
Yeah.
Oh gosh. I'm lucky I have you folks to tell me that. Otherwise, it'll be 1 hour talking about it without sharing the screen. Here you go. July 10th, 2023. Okay, so we're going to start chapter 38, photons and matter waves. Introduction to quantum mechanics, right? There you go. There's a matter waves here, 38. Introduction to, a better title would be Introduction to Quantum Mechanics, or how the microscopic world functions. Before quantum mechanics, we had thermodynamics combined with electricity and magnetism. That's what we would call the classical theory of the microscopic world. Classical theory of the microscopic world. Those were the theories because before the beginning of the 20th century. The theories before the beginning, right? Of the 20th century. Special relativity and quantum mechanics. Mechanics are the theories of the 20th century. If you want a background, a historical background of the beginning of these two theories, come on. It's a very nice TV series. I watch it. There is a very nice TV series about the life of Albert Einstein. Is a 11 episodes. It's a National Geographic TV series. National Geographic TV series. It's just one of the TV series in this called the TV series called Genius. It's about the life of several different geniuses, including Albert Einstein. The one on Albert Einstein is 11 episodes. And they dramatize the relation between Albert Einstein and the guy that founded quantum mechanics. His name was Max Planck. Today we have a very important research institution there in Germany called Max Planck Institute, honoring the contributions of Max Planck himself. Let's take a look here at the internet. TV series, National Geographic TV series. Series Genius. You got? Let's see if we can find watch full episodes. What did you say? What Genius? Okay, and all seasons. They have all seasons here. I don't want. I like Wikipedia. Let's go to Wikipedia. Most likely, you also have that on IMDb. Okay, it's American anthology period drama television series, right? Which premiered on National Geographic. The first season, which aired between April and June 2017, followed the life of Albert Einstein. That was the very first one. From his early years through his time as a patent clerk. Remember, Einstein, he couldn't find a job as a university professor. People didn't think he was good about physics. So he had to find a job as a patent clerk. And who found this job for him was his father-in-law. But then he came to a point that he couldn't hold that job. He couldn't hold that job because he was concentrating on something else. He was concentrating on theoretical physics. But he was a patent clerk there in Switzerland. Okay? In Switzerland. That's where he used to work. But the interesting thing about Einstein is that he was exposed to all sorts of technologies that were being patented at the time. And that made him start thinking about special relativity. But Einstein's contribution didn't restrict it just to special relativity. He came up with other theories as well, including a theory that is related to the work of Max Planck himself, which was the photoelectric effect. Okay? From his early years through his time as a patent clerk and into his later years as a physicist who developed the theory of relativity. This is based on the 2007 book, Einstein, His Life and Universe by, this guy here, Walter Isaacson. He is always writing books about biographical books. Okay, the second season, which aired between April and June 2018, a year later, right, was about Pablo Picasso. Okay, and then the third season, Mary Shelley, right? Mary Shelley, but it was changed. The season was originally supposed to focus on Mary Shelley. Okay, but this was changed during development. We're not interested in that, right? We're interested about this TV series on Albert Einstein. And the whole TV series shows the relationship between Albert Einstein and Max Planck. They didn't know each other, but Albert Einstein was able to follow Max Planck's results through the papers that he published. And he discovered even more. And using the theoretical basement that Max Planck introduced at the time, Albert Einstein himself was able to discover, to make even further discoveries and advance the science even further, just by looking at Max Planck's results. And there is an interesting interaction between Einstein and Max Planck in the TV series that shows that Max Planck, when he wrote his paper, he didn't give much thought about what his theory was all about. He thought it was just like a phenomenological type of theory that luckily ended up explaining the real universe. Okay, But then Einstein thought otherwise. Einstein thought otherwise because he was able to use Max Planck's theory to explain other phenomena like the photoelectric effect. The phenomenon that Max Planck was able to explain was a problem that physicists was struggling at that time, was the black body radiation problem. And on Wikipedia, I also have an article about that. So that's where quantum mechanics started, okay? So this, what I'm gonna talk here, I'm a little bit, I prefer to start this treatment with this section 38.4. For some reason, the book started with the photon and quantum of light. But here is exactly where we should start this discussion, okay? And then we go back to the other one. The historical, that would be the historical chronology of quantum mechanics. So we start with section 38.4 in the book. Okay, and the birth of quantum physics. The birth of quantum physics. Okay, and let's talk about it started with the problem of the black body radiation. Black body radiation problem. We start with the black body radiation problem, like that. A problem that classical physics could not explain appropriately. That's the struggle that was happening. Remember, physicists at that time, not only they were struggling with the problem of the black body radiator, but they are also struggling with the problem of the ether, the luminiferous ether, right? And the negative results that Michelson obtained with his interferometer. And every time that you have a negative result, you either don't publish, okay, or you don't believe it, your results. But fortunately, Michelson published his results with the interferometer that he had, right? And that's what gave support to Einstein's special relativity, theory of special relativity. But let's talk about the black body radiator. What is black body radiator? You have to understand what a black body radiator is. And there are some really neat demonstrations about black body. Let's take a look at black. We have a black body radiator there at LA Harbor College. It's a very simple device. It's amazingly simple device. And at the same time, it's not just a simple device. It's a device that provides a result that's surprising, completely surprising. Radiator. But I want the YouTube. Hopefully we can find something in YouTube. Black body radiation physics. Let's take a look. Demonstration. I want a black body radiator demonstrator. Demonstration. Let's see what they have here. No, wait a minute. Let's go slowly here. Okay, but before we start with the movies, right? I want you to imagine a black body radiator. What is a nice down-to-earth black body radiator? What is a nice demonstration of a black body radiator? Just picture yourself a box, We have one of those there at the Lake Harbor. I always show to my students when I'm teaching physics 39. This box, cardboard box, okay, has aluminum foil here inside, highly reflective surface, reflective inner surface on the inside of the cardboard box, okay? And it can be open and closed. We can open and close it. And on the top of that, we punch a hole here into this box. If you have the box open, you're going to see a very reflective surface, a white surface, a shiny surface that reflects light. But think yourself, if you haven't seen that demonstration before, what do you think is going to happen if we close the box? Okay, what do you think is going to happen when you look through this hole after you close the box? Remember, the surface here is a very shiny, reflective surface. And that's the amazing property of this object, okay? There's a property related to that, to this little hole that you have here. Think what you are going to be able to see, okay? So when we close the box, something surprising happens. Even though the inner surface of the box is very shiny, is very reflective, okay? What you see through this hole is going to be pitch black, okay? That's the surprising characteristic of a black body radiator. Why? And there's a very important, very simple and important explanation for that, okay? While the box is open, light is going through this box, through this opening here, right? This large opening, and it's being reflected by the surface. And you'll be able to see some light coming out here too, okay? But the moment that you close the box, no light, no external light is going to be able to enter the box. If any light enters through this pinhole, this light is going to be trapped inside, reflecting multiple times without finding a way out. That's why you end up seeing a black point here inside, even though the surface on the inside is shiny. It's reflective, very high reflectance surface. You believe that? Okay, so let's see if we have a demonstration here. I want to see one exactly like the one that we have. This one is a more advanced setup. It's not the one that I want to show you. Yeah, you can see that, not this one. Okay, so black body demonstrator. Let's say black body demonstrator. Black body radiation demonstration. Let's see. Let's see here. Oh yeah, this guy, the box. Okay.
Before you get to the ball, turn it. One shot. This is an example of a black body, so-called.
Do you see the hole here? He starts with the box closed, but do you see here the hole is completely black, pitch black, right?
It's not black.
But what about the inside?
White interior.
Look at the inside. It's actually white paper. You can do that also with an aluminum foil, highly reflective aluminum foil.
But
and take a look at the hole. And let's go back a little bit here. Okay. See here the hole. You know, it is transparent. There's nothing. You know, there's nothing in the way here.
But it serves as a good example of a black body for the following reason. Light that comes through this hole is reflected around inside of the box and has a hard time getting back out before it.
So remember, in order for you to see an object, and if you want to see an object at naked eye, that object must either emit visible radiation like it happens to the sun, or it must reflect visible radiation. The human eye is sensitive only to visible radiation, only to visible electromagnetic waves. The human body and other types of bodies here on the earth, right? They are emitters of infrared radiation because of their relatively low temperature, okay? And if we turn off the light in the room, we wouldn't be able to see anybody because there is no visible light for us to reflect. Keep that in mind, okay? However, if you had infrared vision, if we had infrared vision like many soldiers have whenever they are fighting there in the battlefield, we would be able to see each other in the dark. If you're following the Ukrainian-Russian war, okay, there's some interesting development of that war, right? The Russians doesn't have as much as an advanced technology in the battlefield, even compared to Ukraine, not compared to Ukraine, compared to the Western civilization, United States and the Europeans, right? And NATO is providing infrared vision to the Ukrainians to fight the those battles that they are having right now in the war. And so what the Ukrainians are doing right now, they're making much of their operations during the nighttime because they can't see in the dark, and the Russians cannot see in the dark, and they have been far more successful operating during the nighttime than the Russians have, okay? And that's why. Why is that? Because the human body is at a typical temperature that emits infrared radiation. We cannot see infrared radiation with the naked eye. We can only see visible light with the naked eye. So that's the problem that the Russians are having. To fight at night, they must have infrared vision. Since they are operating with the naked eye during the night, they are having a hard time to fight the Ukrainians.
It's reflected several times. So
any radiation that's escaping this black body here is not going to be visible light. It's going to be infrared light. Again, why is that? Because any light that goes through this hole is going to be reflected multiple times inside. It's going to be trapped there inside. It's not going to find its way through the hole. If it found its way through the hole, then you would be able to see some visible light coming from the black body radiator, okay?
Effectively, even though the interior of the box is white, the image that you see through the hole is black. And that's an indication that the light, that all of the light that comes through this hole is actually absorbed by the body itself.
It's absorbed by the cavity inside the body, okay? That would be a better way of, and I would even say more, not just absorbed, but also trapped, because it's not 100% absorption here. The radiation keeps reflecting back and forth inside this cavity and doesn't find a way out.
Black bodies are important because once they've absorbed all the light and they don't reflect any, they actually then emit radiation according to the black body spectrum, and according to their temperature, they have this bell-shaped black body spectrum that they emit out into space. This is at a low enough temperature that the black body spectrum is not visible, but an incandescent bulb, for example, is at a high enough temperature that its black body spectrum is visible to the eye and actually involves some heat and infrared light as in heat, as well as ultraviolet light that will come from those sources. So this is a demonstration of the black body spectrum.
It's a very simple demonstration. Now you can do something like that at home. Get a cardboard box, place a aluminum foil there inside, get a lid, make a hole in that lid, and play with the sizes of the hole of the lid, right? There will be a point in which the hole is going to be so large that you will start to see some visible light coming from the inside of the body. That's why it's called the black body radiator, right? Because you don't see any light coming out of it. So that's the idea. Here you go. Another explanation of the black body radiator is this is a idealized black body radiator. Is a cavity. Doesn't have to be a cavity that is parallelepiped, right? Or a cube. It can be any cavity with a little pinhole there inside that let light go through. And according to geometrical optics, this light is reflected here inside and trapped. Hardly find any way through the hole, so you could see with the naked eye. That's why it looks black on the inside. That's why the black body, this cavity, looks black. Doesn't matter. Now, if you go ahead and put a source here inside, okay, you might be able to see light going through. So let me explain, let me document everything that I told you about the black body. Okay, black body radiation problem. Okay, by definition, notes. A black body is an object that produces its own electromagnetic radiation and does not reflect anything. Okay, that's what the ideal black body radiator. Remember, we have reflection of light, and you have also emission of light. One thing is different from the other. Okay, reflection of light is light that is incident on an object. It's light that comes from one object and is incident on another one. Another one, okay? And then you have emission of light. It's a radiation that comes from that originates, right? Originates from the object itself. A black body does not reflect light at all, right? And one way to do that, one way to create a black body is by having a cavity with a small aperture at its surface. This object okay? And how do we understand this black body in terms of the physics? How black bodies can be understood in terms of physics? How black bodies can be understood in terms of physics. Okay. Okay, you have to think in terms of thermodynamics. You have to think in about, right? Thermodynamics. Going back to our course in thermodynamics. According to our thermodynamics course, there are three ways to transfer heat energy, to transfer heat. Okay, three ways to transfer heat. One is by conduction. Remember that? Which require physical contact. Another way is by convection, which require the movement of masses. And there is this other third way that is more important, is by radiation. When we talk about radiation, we are talking about electromagnetic radiation, which can be radio, anywhere between radio waves through the microwave spectrum, infrared, visible. Remember, you have to have that memorized, right? Visible, light, ultraviolet. Remember, infra, right? See here? Infra and ultra, right? Infra, below the red. Ultra, past the violet or past the blue. Okay? Ultraviolet, X-rays, and gamma rays. Those. So what we're concerned here is this type of heat transfer, which results in electromagnetic radiation. That's why it's called radiation, because it has to do with electromagnetic radiation. We don't have electromagnetic radiation here. We don't have electromagnetic radiation here. Three different ways of transferring heat. Okay, so your black body radiator is radiating at a wavelength that is invisible to the naked eye because it is of a very low temperature. This is a room temperature. By low temperature, I mean by room temperature. It's at a room temperature. Because it's a room temperature, the only radiation that your black body radiator is going to emit is going to be in the infrared region that is invisible to the human eye. That's why we see it black. Make sense? Okay. And then perform the thought experiment, right? I'm gonna perform the following thought experiment. Perform the following thought experiment. I'm documenting here because I didn't document before, right? I already told you about that. So let's just repeat, right? Perform the following thought experiment. You already know. You already know. So that is going to give you an idea of the difference between radiation, right? Emission of radiation and reflection of radiation, right? You already know that when the lights in a room is off, we cannot see anyone in the room. And the reason is that's because there is no light to reflect by each object. The lights in the room are off. We cannot see anyone in the room. That's because there is no light to reflect by each object. Instead, we emit light. We emit electromagnetic radiation at a wavelength that correlates with our temperature. 36 degrees, close to the room temperature, right? 36 degrees C, which is close to the room temperature. Since we do not have infrared vision, we all appear black and cannot see anyone. We cannot see anyone. That's the important idea that you must have in your mind to understand black body radiation. Now, what about which other types of radiators, black body radiators, do you have out there? Okay, in addition to that one, to the idealized one. Okay. Okay, another example of a black body radiator is the surface of any star. But this is an approximation, okay? Let's put here. This is an approximation. The surface of a star is an approximation to a black body radiator BB. Why is that? Why is that? That's because, that is because there are no other stars. The sun, right? Another example is the surface of the sun. Let's put here. Of the sun, right? Or any star. Or any star. That's because there is no other star nearby to illuminate the sun, right? So it can reflect light. For this reason, any radiation that we see from the sun is due to its own emission. Okay? And there's a reason why we say that. Let me show you why, okay? And I'm going to give you an example. This book has a very nice example here. Let's see if it's here. Oh, no, it's not here. Let's see. No, it's not here. It's on here. Let's see if I can find it. Oh, yeah, here you go. It's Wikipedia, okay? Everybody's familiar with the blacksmiths, okay? What blacksmiths do? They warm up iron, right? And steel. And when they warm up iron and steel, it gets so hot, that the iron starts to emit radiation at the visible region, in the visible region. Most of it comes from infrared, but there's also some visible. That's why this sample here of steel is glowing, okay? And through their trade, blacksmiths, through their trade, they manage to relate the color of the sample with their temperature. And here we have a color chart of the temperature of steel. Okay? If this sample is emitting, appears to be black, right? This color here. That's because it has a temperature of 550 degrees and lower. Okay? I'm gonna put that. So this guy is emitting radiation like a black body. He's not reflecting. Whatever it is reflecting is very little. But if it's reflecting anything, all you can do is put in a dark room. Okay? The radiation that it emits is far more than the radiation that it's reflecting. It has everything to do with how much radiation is being reflected compared to how much radiation is being emitted. As the color becomes not darker but lighter, that means that the temperature is increasing. At the color brown, the brown color is going to be 630 degrees. At this color here, approaching the red, right? 680 and so on. The brighter the color, the higher the temperature. That's why we can see light from the sun, because the temperature of the sun is very high. Actually, the temperature of the sun is more than 1300 C. It's more like 5,000 C. The temperature of the surface of the sun. Here you go. The sun with an effective temperature of approximately, don't forget, it's Kelvin. He's talking about Kelvin. In Celsius would be around 5,500 Celsius. Okay, so that's how a black body behaves. So the higher the temperature of a black body, I'm gonna put dB, the easier it is to see its emission. Okay? That's why incandescent light bulbs emit light. Yep. That is why incandescent light bulbs emit light, because their filament is very hot. We pass electricity between the filaments. The filament has a given resistance, and it starts to warm up to a point where it's so hot that it starts to emit light. But by the way, incandescent light bulb emits most of its radiation in the infrared spectrum, okay? Not in the visible, but in the infrared region of the spectrum. The temperature is not high enough to emit in the visible. Let's take a look at Wikipedia. Incandescent light bulb. Let's see what's the temperature, right? Incandescent light bulb temperature. Color temperature, we should roughly 4,600 Fahrenheit. 4,600 Fahrenheit is half the temperature of the sun. 2,300 degrees C, more or less, which less than half of the temperature of the sun, of the surface of the sun. 2,000 degrees C. At 2,000 degrees C, it emits mostly on the infrared. Okay. Spectral distribution. Let's take a look. Spectral distribution. Incandescent light bulb spectral. This is spectrum. Here you go. Incandescent light bulb spectrum. Let's see here. Depend on the lamp, right? Let's see. Mercury vapor lamp. See, it's in this region. It has two peaks. The mercury. What about incandescent? Tungsten lamp. Tungsten lamp is kind of incandescent light bulb. White LED bulb. We don't want white LED. I want an actual incandescent light bulb. The visible light spectrum of the white light emitting diode is represented by the green curve. Okay, that's the white light. But I want smooth sunlight. Yeah, let's stick with tungsten. Tungsten is like a incandescent light bulb. Note that the emission, the relative energy emission of a tungsten light lamp is mostly into infrared. The peak is going to be the infrared. Okay, you should expect to have something like that extending into the infrared with a peak in the infrared. Okay, let's take a look at incandescent. Incandescent tungsten, yeah? See that? Incandescent tungsten devices. Incandescent light sources. Let's see if they have the spectrum here. No. See, the candle is an incandescent, is a source of incandescent light. Incandescent. Yeah, here you go. That's the one. Tungsten and halogen lamps. But we already saw how the emissions looked like, right? For the tungsten. Physics of light. Let's see if we have a better chart here. Emission spectra of different light sources. Okay, let's see. Yeah, that's the incandescent light bulb. I cannot zoom into this one. It's difficult to see the wavelengths here. But basically what we have blue, green, and red, right? And notice that a very small portion of the spectrum, though this spectrum is usually like in a bell-shaped format. That's for the incandescent light bulb. This one seems to be the fluorescent, and that's another one that's fluorescent. They're very similar to each other. See that? Those are not incandescent, right? They're fluorescent. It's a different type of phenomenon. But we want to stick to this one here. Like I said, this one right here. It doesn't show the whole spectrum, but just a part of it, you know, which shows that most of the light is emitted in the infrared. Here is 700. I can finally see it here, 700. He cut down the emission spectrum at the infrared, at the red. Okay. Emission spectrum, incandescent tungsten light bulb, okay, and so on. So the higher the temperature of black body, the higher the temperature of a black body, the easier it is to see its emission. Because their filament is very hot. On the region around 200, 2,500, 400 degrees C. Why this problem is important? Okay? Why the problem? Why the problem of the black body radiator is important, right? Is important in physics. Why is it? There's a reason, right? And I already mentioned that at the turn of the 19th and 20th centuries, physicists could not find an explanation, a proper theoretical explanation, right? A proper theory that would explain the problem of the black body radiator. That's why. Okay. And let me explain one thing that they knew. One thing they knew from a theoretical standpoint. Standing point was the so-called Stephan's law. Remember that? Stephan's law related the temperature, the power, not the power emitted by a black body. Insert equation here. If you always do that to me, the power emitted by a black body, you know, that again, an idealized black body was proportional to the force power of the temperature. Can you remember that? Strictly speaking, not the force power of the temperature of the black body, but the difference of the force power with respect to the surrounding environment. Temperature of the black body, okay, T is the temperature of the black body, and T naught is the temperature of the surrounding, of the environment surrounding the black body radiator. Okay. If this temperature of surrounding environment was the same as the black body, so the black body wouldn't emit anything. If the temperature of surrounding environment was greater than T, then the black body just would absorb and wouldn't emit anything or even reflect, right? So the black body has to have a temperature greater than the surrounding environment for it to emit light, to emit radiation, electromagnetic radiation. Okay, remember that? That was that can be derived using electromagnetic arguments. We're not going to derive it, but I want you to memorize that. This theoretical result worked well. This theoretical result worked well. They managed to derive it and found exactly what the theory, what the experiment would reflect. Okay. Another important successful theoretical result was Wien's displacement law. Wien's displacement law stated that black bodies radiators, black bodies radiators, oh gosh, I'll do it all over again. Yeah. Black body radiators had a peak temperature with a maximum intensity, which is the wavelength at the maximum intensity, proportional to the inverse of the temperature of the radiator. That was another successful theoretical result. Can you remember that? It's not difficult to memorize, right? Force powers of temperature, inverse values of the temperature. And what does it mean? You know, you go ahead, get the radiation comes from your black body, put a prism, either a prism or a diffraction grating in front of the source. Either the prism or diffraction grating would decompose the white light comes from the black body radiator, and one of those wavelengths would have a higher intensity. Okay, like the sun. The sun emits more on the yellow than on the green or the red or the blue. Okay, there are some stars that emit more on the blue than the other colors. There are some stars that emit more on the infrared than some of the other colors. It has everything to do with the temperature of the star. And don't forget, this is a proportion. This is a proportion. Okay, notice the colder the object is, the longer its wavelengths. Okay? 5,000 degrees C correspond to the yellow region of the spectrum. And we're going to elaborate more on that. Okay? That's just part. What was really, what was really challenging, even though these two results were successful, right? What was really challenging was to determine the spectral radiance of the black body. Was a theoretical model of the spectral radiance of a black body. for you to understand what I'm discussing here, you have really to understand what we did there in gratings and prisms, right? That phenomenon of dispersion, light dispersion through a prism, how gratings work. Gratings manage to separate different wavelengths color. And that's what we are discussing here. So scientists were using those devices to find out the spectral behavior of the sources. A theoretical model of the spectral radiance of a black body. So what's the spectral radiance of a black body? Let's take a look here. Your book gives a very nice explanation of the spectral radiance. What's the definition, right, of spectral radiance? Not this one, huh? Here you go. Okay, that's what the spectral radiance is all about. It's the intensity of the light source. Remember, intensity, what is intensity? Intensity is power over unit of area, right? Divided by unit of wavelength. That's what spectral light, spectral radiance is all about. So what is spectral radiance? Okay, what is spectral radiance? Okay, I'm gonna put the notation of the book. Spectral radiance of different sources is a function of the wavelengths, by the way. And it is, I'm gonna put a quality here, is intensity of the light source. And let's not forget that is also a function of the wavelengths, right? Divided by the wavelength itself. And by the way, what is intensity? Intensity is power, which can be a function of the wavelength as well, divided by the surface area. Surface area of the radiator. Okay, that's what it is. What was the result that the scientists were obtaining when they derived the spectral radiance of a black body using classical mechanics, using electromagnetic theory and thermodynamics, plus, of course, mechanics as well, classical mechanics? You're getting something like that, you know? You're getting something using classical mechanics. Physicists were getting the following result for spectral radiance. They were getting something that was proportional to the force power of the wavelengths. Okay, I'm gonna put that's what they're getting. And I'm going to, this result, you know, this result explained pretty well the behavior of low temperature black body radiators. But as their temperature increased, think about that. They could have, they usually would do that, those experiments with hot iron, right, or hot steel, just like you saw in the Wikipedia. Here, not this one. Where's that? Here you go. This one here. Okay. Think about the scientists performing this experiment. They would hire a blacksmith that was very skillful, and warming up a piece of steel, they would get the scientists would get their diffraction grating, would decompose the light coming from this hot source, and would measure the intensity of each of the wavelengths that they would see in the screen that they were seeing the screen. Okay, can you picture that in your mind? That's what the scientists were doing. Maybe they would be doing that, for instance, with hot steel or other types of metals, not just steel. Could be iron, could be even coal. Okay, you get the coal, right? You would warm up the coal, and what happens? It would emit the red light. So those were good black body radiators, and the scientists were performing experiments with those materials, including their diffraction grating, including their prism to decompose the light, the radiation coming from those objects. Okay, and when they were doing those experiments, what they would get, I'm going to show you what they would get. And the book has a very good illustration. Okay, they would get a picture, a spectral distribution that was somewhat like that, kind of a bell-shaped. It's not exactly bell-shaped. Okay, in this specific case, the peak intensity was in the infrared, 1.5 microns. The visible spectrum is right in here. Do you remember that spectral distribution of the incandescent light source that I showed to you? Right? Matches what you see right in here. Let's see if I can find that again for you. Here you go. This one, right? Here you go. This one. Figures, download, not this one. Here, I gotta click on this one here. Okay, that's the part of the incandescent light bulb. They measure, in this case, they measure only up to 700 nanometers. In their book, they have the full illustration of how this spectral distribution look like, right? Here's around 700. That's where that picture stops. That picture stops in this region. But if you measure past 700, you would observe this type of spectral radiance. They'll find a peak around 1.5 microns for this specific black body radiator. That was the experimental result, and that's what the classical theory predicted. Inverse of the wavelengths, inverse of the force power of the wavelengths. At those wavelengths, yeah, the classical theory was pretty good. But then as you move towards shorter wavelengths, towards the ultraviolet, the classical theory would diverge completely. That's what we call the catastrophe of the ultraviolet catastrophe. The scientists would call the ultraviolet catastrophe. Going back, or right, take a look here. Classical mechanics. And by the way, I'm going to put between parentheses here the derivation of the formula below is very difficult. Okay, so I'm presenting just the final result. The behavior of the black body at low temperatures. But as their temperature increased, the divergence would be large. The so-called ultraviolet catastrophe. Okay. And let's, I think it's a good point to stop right now. And let me take attendance. Any questions about that? That's the historical background. That was the dilemma that physicists had at the time, at the turn of the 20th century, from the 19th to the 20th century, okay? And then came Max Planck. He managed to explain everything, and we are going to cover that after the break. Let's see. Sydney, are you there? Yeah, thank you. Amy? Thank you, Amy. Andy? Andy? Andy, okay, I see Andy here, so I'm gonna put a star here in his name. Alex Hernandez. I don't see Alex here in my list. Sartak? Here, thank you. Next is Basilio Lopez.
Here, Professor.
Thank you. Joshua Mohan.
I'm here.
Thank you, Joshua. Oops, what happened here? Zaid. I don't see Zaid in my list. Huh. Oh my, oh gosh, what happened here? Oh, let's start all over again. My computer is starting to misbehave. I do not know why. Cannot be open or repair. Oh my goodness, cannot be open or repair. Okay, gotta start all over again. What's going on here? Ay. This one. Okay, I'm gonna start all over again. Sydney is here, right? Amy is here. Andy is here, but he's not answering. Alex Hernandez is not here. Tartak is here. Yeah, let me save it before Basilio is also here. Jeshuan is here, right? Yeah. Oh gosh, it's happening again. Undo. Let's see. Not supposed to be doing that. Zaid not here. Sumana just arrived. Let's she settle down and I'll go back to her. Alisa, are you there, Alisa?
Here.
Okay. Karsika? I can see Karsika here in my list. I'm gonna put a star in Kartika. Sumana, are you there? Can you hear me? Yeah, okay, good. Mary. Hello, Mary. Put a star in Mary's name here. Raymond. Thank you, Raymond.
Professor.
Who is that?
Here.
Ashley?
Great.
Ah, okay, Ashley. Hi, okay. Kyriakos? I don't see Kyriakos. And Alexis Madrigal. Hello, Alexis. Alexis is not answering. So let's see what is. Sumana, are you there, Sumana? Oh yeah, okay, Sumana is here. And Nukala, right? Let me make sure I got it. Yeah, I put it here. And Andy, are you there? Andy, one more chance before you go into the break. Okay, Kartika. Another chance here. Mary. Mary. Yeah, looks like Mary left, huh? Oh, here you go. She's back. Are you there, Mary?
Professor, I'm here.
Who is that? Who is that, please? Okay, well,
I'm here, Professor.
okay, Mary, right? Okay, good. Who else? Who else mentioned here? Alexis, let's see. Are you there, Alexis? Okay, so there are 3 students who did an answer. 1, 2, 3, 10, 13. Yeah, we have it here. So let's go for our break. Notes. Okay, let's do 1:15, right? No, it's not 1:15, sorry. 9:15. 9:15 a.m. to 9:30 a.m. Kartika? Kartika, right? Let's go. Anybody else? Alexis and Andy. Okay. I'll leave this way and I will see you in a little bit more than 15 minutes. Okay. Okay, so now let's take a look how scientists, let us take a quick qualitative look at how classical physicists, right, were solving the black body radiator problem. Okay, let's take a quick look. Okay, Alexis, okay. Let me attend this to Alexis. Alexis, because now we have 13 here in my list. Someone left, huh? 2 students left. Okay, we'll figure that out later on. Okay, let's take a quick qualitative look at how classical physicists were solving the black body radiator problem. That's something that you have to know as well. Okay, the model. What was the model, right? What was the model of the black body radiator? Okay, that they were using. Was it correct? Was the model correct? If the model was not correct, maybe the model was not correct. That's why they were having that result, that strange result of the ultraviolet catastrophe. Or, since the theoretical result was not reflecting reality, then there were 2 possible explanations, right? One, either the model they were using was not correct. I'm not going to discuss the model, or right? Or there was something else, something fundamentally incorrect about the laws of physics. Okay, just like Michelson, right? When Michelson was doing his experiment, he obtained a negative result. He was expecting to obtain a positive result. He couldn't find an explanation for that. So, either their model that they were using was incorrect, or there was something fundamentally incorrect about the laws of physics, or, there was a third possibility, or just both of them, both of the above, both of the above, right? In the case of Michelson-Morley experiment. Okay. Both the luminiferous ether model ether model was incorrect, right? And the fundaments of physics that were being used, fundaments of physics that were being used were breaking down as well. In the case of the relativity, the special relativity, right? And special relativity and the Michelson-Morley experiment. And the fundamentals of physics that were being used were breaking down. So let's see, let's take a look at the model that they are using. The model they are using were very simple. The model for the black body radiator they were using was very simple. One, the radiation coming from the black body inner wall was due to electric charges oscillating inside the wall. That was the model. Since these electric charges were oscillating, right? Then they were emitting electromagnetic radiation. Okay? Remember, any wave is associated with an oscillating object, with an oscillating particle, right? So an electromagnetic radiation occurs whenever an electric charge is oscillating back and forth. Or just like in the case of the AC circuit, right? The electric charges oscillate back and forth and produce an electromagnetic oscillation. If you have just a steady current, you don't have an electromagnetic radiation. You have just a magnetic field, a static magnetic field. But if you have an electric charge that's oscillating, or even better, not just an electric charge oscillating, but an accelerated electric charge. The electric charge does not to be necessarily oscillating. Does not to have to necessarily oscillate to produce an electromagnetic radiation. It can also be, you can also accelerate an electric charge. And an electric charge that oscillating is accelerating. Oscillation is just a special example, one example of an accelerated charge. Since these electric charges were oscillating, then they were emitting electromagnetic radiation. That was the model that they were using, and here's an illustration of the model. Here you go. All matter is composed of electric charges, electrons, protons, neutrons, right? Neutrons don't have an electric charge. At the time, physicists knew about electrons, and they come up, well, look, we must have some electrons that are oscillating because of the temperature of the black body radiator. They also knew that the higher the temperature, the higher the oscillation of the electric charges. Make sense? The lower the temperature of the black body oscillator, the lower the amplitude of the electric charges. And because those electric charges are oscillating, they are producing electromagnetic radiation. That was the assumption, the important assumption. Okay? But then they said something else too, okay? Since these electric charges were oscillating, they were emitting electromagnetic radiation. Okay, the energy of these charges, according to classical mechanics, right? You already know that. Is given by what? You know, I'm gonna write that down for you. You already know that. Oh, you already know that. Half K amplitude square of the charges. And this K, you know, would be a parameter that they could find for the electrons that were oscillating there. The amplitude, they would make some assumptions, okay, on the amplitude of the electron there. And so by using this formula of the energy levels, we say the energy levels, okay? This is the equation of the energy levels of the classical charges. By using the above equation, they obtain the proportionality of the spectral radiance. A very simple model. So the question is, the spectral radiance is not matching the experimental results. So what's happening here? Is this model incorrect? Is this model of the electric charge oscillation is incorrect? Right? Or there was something else fundamentally incorrect about the laws of physics, or the problem was both of them. Okay, the solution proposed by Planck. Solution proposed by Planck, Max Planck. And you know, he published this paper in 1900 with a paper he published in 1900s, which is considered the year quantum mechanics was born. The year that quantum mechanics was born. Was the following. One, he did not discard the oscillating charge model. He didn't discard that. Okay. Remember, here you go. Oscillating charge was this one. And very important, there is an important consequence of this classical oscillator, right? The importance of this classical oscillator is that the energy levels of those electric charge could assume a continuous level of continuous values, continuous spectrum of values. Okay, that was dependent only on the amplitude of the oscillation of the charge. Okay, Max Planck didn't discard this model. He said, "Oh, that's good. We're gonna keep it. We're gonna keep this model." But he made a very. So what did he do? What did he do that was innovative? That was unique at the time. Okay. Instead, however, instead of using the classical oscillator model for the energy, okay, he assumed that the energy of the electrons had a different relation. And the moment that he published this model, that's when the classical ideas of physics start to come apart. Instead, so I'm gonna put it here. Instead of half Ka squared, which again is the potential energy for a classical oscillator, right? He said, look, folks, let's try something different. Let's not trash the oscillating charge model of the electromagnetic radiation. We know from electromechanics, from electrodynamics, we know from the Maxwell's equations that an oscillating charge, an accelerated charge, produces an electromagnetic radiation, and this theory is very successful. We have been very successful with it. So instead, using this half Ka squared, he said, let's assume that instead the energy of those oscillators, of those electron oscillators, is given by this equation instead. Okay? Where n is an integer number, where n is equal to 1, 2, 3. Right? I'm gonna put it here. Where n is equal to 1, 2, 3, etc. F, etc. F is the frequency of oscillation. Right? And H is a magical, let's say, at that time was considered a magical, right? A magical constant that today is called the Planck's constant. Max Planck's constant, in honor of Max Planck. And then he made, okay, with this simple assumption, he rederived the spectral radiance. All he did was to substitute this value here, this equation here, by this equation. He derived the spectral radiation and obtained the following result. Okay. You obtain something like that. Equal, right? 2 pi hc squared. Do you see the velocity of the light showing up here? Isn't that amazing? The velocity of the light is showing up in there. Just like it happened with relativity, special relativity. Lambda to the 5th power. Okay. Notice that we had lambda to the 4th power, right? Inversely proportional to the 4th power. Here, Max Planck is getting inversely proportional to the 5th power. So far looks worse than what we had. But it's not worse because there's something else here. There's something else here. He also found, after his derivation, that there was an exponent, hc, velocity of the light again here, divided by the wavelengths. The wavelengths. The wavelengths. There was this constant that we call the Boltzmann constant, and the temperature. Okay, there's more. -1. That's the whole story about the black body radiator. And when he compared this theoretical result with the experimental result, he got a match. Okay, so let me write down what H is. H, where H is equal to 6.626 times 10 to minus 34 joules second raised to the power, okay. Compare side by side. We go side by side. I'm gonna write down the complete result here. So 2 pi c. So you can 2 pi c kBt, 2 pi c. That's the Boltzmann constant times t. Okay. That would be the classical result. Classical result. Compare the above with the classical result. This one and this one. Now let's plot that. I did plot that for you, by the way. This curve that you see right in here is a plot of the Planck's result. If the black body radiator is at 300 Kelvin, which is room temperature, you have a maximum wavelength, a peak emission of the maximum wavelength is around 10 microns. What you see here is 10 microns. 10 times 10 to minus 6 meters. Oh, see, no, the problem is just 1 minute here. My battery, it looks like my battery ran out. Right in here. Here you go. At 400 kelvins, which is also close to room temperature, 10 degrees above room temperature, we have the peak shifting towards shorter wavelengths. See here? That's what the lambda maximum is all about. That Finn's relation that I mentioned to you. Okay? Whereas here is the result of the classical theory, red and violet, right? 300 kelvins, 400 kelvins. And that matches pretty well the experimental result. See that as the temperature increases, the lambda max shift towards ultraviolet. The ultraviolet shifts towards shorter and shorter wavelengths. And again, what you see here is the ultraviolet catastrophe. This theory works well in this region, but then start to break down for shorter and shorter wavelengths. Let's see if we can get a simulation here. Let's see, I came up with a nice model that we can, in Excel, that you can play with. Let's see here, simulations right in here. Let's see here, oscillation, black body radiation. Okay, here you go. Classical Planck theory. right? Here you go, that's the wavelengths. Going from 2 times 10 to minus 7. 2 times 10 is what? 2 minus 7 is 10 to minus 6 is 20 microns. Let's see here, 2 times meters, right? It's 20. Oh, it's not. Oh my goodness, everything is failing today. Sorry, folks. I don't know what's going on. Here's my computer. Yeah, see, it crashed for some reason. Oh my goodness. Okay, I don't know why is that. So 20 e to minus 8, right? And then which is also 200 e to minus 6, 200 microns, which is also 0.2 e to minus 9. No, it's not 0.2 e to minus 9. 0.2 e minus 10. 0.2 e to minus 10, right? No. 11. 0.2 e to minus 6. Okay. 0.2 e to minus 6. That's what it is. This one is supposed to be, yeah, this one is not correct. 0.2 e to minus 6 is 200 nanometers. Okay, what you see here is 200 nanometers. 200 nanometers is UV. Okay, from the UV all the way down to, I plotted all the way down, man, past the 10 microns. Yeah, past 10 microns, right? From the UV to the infrared. And the equation, oh, here you go, here's the frequency, right? If I convert the wavelengths into frequency, that's what you get. Now, what about that? This term here is what goes upstairs in the equation. 2 pi f2. F2 is the frequency, f2 to the fourth power, right? F2 to the fourth power is the inverse of wavelengths. And then 2 pi, p down, p up, and p down, that's Planck's. Planck's is this term here multiplied by this. Oh, this one is the classical, by the way. This is what is upstairs in the quantum equation formula. Here's the classical mechanics. I did that for 300 kelvins and 400 kelvins, okay? So here you go. 400 kelvins right in here. 300 kelvins, this one right in here. Okay? And if you look at the equation, you have the exponential factor here, -1. Again, you can do that at home if you want to practice. It helps to repeat all those equations that I did. And then you can play with the numbers. I did for 300 and 400. You can do more. Let's see. What about the surface of the sun? Can I get the surface of the sun temperature? Well, let's go slowly, right? Let's see, 500. Let's do 500 first. Yeah, see, 500, the peak goes higher and higher, right? We can even, let's see, one order of magnitude here. Let's see if it, oh, I went too high. I went too high, but all I have to do is to go to 4 times 10 to the 8. 4. Yeah. The peak is being cut down just a little bit. Right? If I want to, let's try 1,000 kelvins. Okay, still not quite see the temperature here, the graph here. And then I have to adjust again my scale. Let's see if I can go to 1 order of magnitude. Not yet, not quite. Another order of magnitude. Okay, too much, right? Now let's put half of that. Oh, too much. So we gotta go to 7 maybe. 9, 8. Huh. 9. That's strange. Let's try it. E to the 10. Let's try it here. Oh, what did I do here? Here we go. Axis option. We gotta go to 10 here. Still didn't get there. Huh? Let's put 11 to the 11. And now it's too much. But you got the idea, right? Here you go. Here's my equation at 1,000 kelvins. We get 0.5. I want to get better. Yeah, still far away. Let's see. 1. Yeah, 2. Good. Now we got it. Here you go. Here's my peak, right? My peak now is a different wavelength. It's 3.26 times 10 to the minus 6. It's still in the infrared, the peak wavelength, because my black body radiator is 1,000 kelvins. If you wanted to go to the visible, let's see if it's gonna fit here. 5,000 kelvins. Oh, went way up. And I believe that, yeah, you should be able to visualize it. I have to change the scale of my axis. Yeah, now the temperature is so high that we cannot even visualize the peak, okay? We cannot even, oh yeah, here you go. Yeah, I'm getting there. The blue curve is the one. Let's try again. Let's keep on trying. 2, let's try 5 here. Let's see if we can visualize the peak. Not yet. 8. Oh, not yet. Let's see, 10. Ooh. Yeah, we are far away, right? So 1.5 times 10 to the 3. That's the power. And you know, the peak that I'm talking about is this blue line here. See, it's going up here and then it's coming down here. I'm going to stop here, otherwise you won't be able to continue, okay? But we can do that at home, and I'm going to bring down this guy to 7. No. Okay. Okay, good. And I bring this one down to 8. Let's see. Okay, yeah. 8, 9. I still have 5,000 here. I'm gonna put 300. Yeah, okay, now we're getting there. We're talking about 10 to the 7. On the 10 to the 8. Yeah. And let's go 10 to the 9. Too much. Half of it. 0.1. Yeah. 2. Yeah. We can. Okay. So again, this is 300. This is 400. 400 Kelvin. that was Planck's result was, okay? So let's now take a look at this plotting. It doesn't matter what the temperature it is, it's gonna be the same, the same genetic behavior. The only thing that changes is going to be the power, right? The intensity is gonna go higher and higher, and the wavelength, the peak wavelength is gonna be shifted towards the shorter region of the spectrum. Okay? And again, this is the classical result that didn't match the experimental result. So let's summarize. Okay. 1, experimental results of the black body radiator indicated a spectral radiance spectral radiance distribution similar to a bell-shaped curve, with a peak located at lambda max given by the Wien's distribution. Okay, Wien's distribution. This one, right? Wien's displacement law. Not Wien's distribution, but Wien's displacement law. Displacement law. Classical theory assumed the radiation was emitted by oscillating electrons having energies given by that of a simple harmonic oscillator. Potential energy, right? Given by the classical theory resulted in the following. Classical theory using the above model resulted in the following: a spectral distribution yeah, didn't work. Yeah. I'm gonna do it this way. Classical theory. No, not. Word document sometimes has this not so nice feature that you can behave oddly. Classical theory using the above model resulted in the following. Okay, this theoretical result diverged completely from the experiment at shorter wavelengths. Planck's solution was to assume that the energy of the electrons, Planck's successful solution, right? Was the sum of the energy of the electrons were discrete or quantized. Okay. Here you go, that's the one. And I'm even going to put a subscript n, discrete or quantized. Assumption turned out to be very successful, explaining the experimental results. And the final formula was this one. Okay, like that. That's the summary, okay? That's the summary. The following, ultraviolet catastrophe. Diverge completely from the experiment at shorter wavelengths. Longer wavelengths, it agreed pretty well. Okay, and so instead of modeling the electrons as a classical oscillator with a continuous values of energy distribution, what Planck's proposed was something else like that. Electrons can have energy levels only at these discrete values. And that's the name of quantum. Quantum means discrete. Can have only this energy level at this value or energy level at this value at this frequency and so on. Okay. Now it happens that this number is so small, but so small that it should fit here in this classical model only if the energy values that we're considering are very large. Okay. And we're going to come up with an example that's very enlightening. An enlightening example. Okay? Example. Let an object of mass m equal 0.01 kilograms attached to a spring of constant K 10 newtons per meter. Find A, its frequency of oscillation. Frequency, here you go, frequency of oscillation. The mechanical energy, its mechanical energy for an amplitude of 0.1 meters, 10 centimeters. The quantum number associated with this energy, with the energy in item B, energy in item B, So let's take a look here. Example, solution. Solution. Frequency, right? Go back to our series on the frequencies given by go back to the equation that we derived for the frequency of a harmonic oscillator. And remember that is going to be 1 divided by 2 pi square root of k over m, right? When we plug in all the values that you see in there, 10 divided by 0.01, Newtons per meter, and then take the square root. What do you get? Let's calculate here in the spreadsheet. Equal 1 divided by 2 times pi square root. Oops. Square root of 10. We are calculating just the frequency, right? We are not calculating the energy yet. 10.01. I'm getting 503. And divided by 0.01 is 1,000. Then you gotta take approximately 1,000, right? Then you take the square root of 1,000, you get what? 1,300, no, it's more, it's 300, something around 300. 300 divided by 6. Let's see what I'm like. Let's do it step by step, right? 10 divided by 0.101, right? 10 divided by, it's 1,000. And then you take the square root of 1,000. 31, around 30. And then you take 31 divided by 2. And then you have to divide it by pi. 15 divided by pi. So that's the step by step. 503 hertz. 5.03 hertz. And then you gotta take the mechanical energy. What's the mechanical energy for that amplitude? Amplitude is okay. This equation right in here. Gotta do this little trick so Microsoft Word behaves in the way it has to behave, right? That I want it to behave. So let's do the math too. Excel. Half times 10 times 0.01 square. That's my classical oscillator. It's not 0.01, it's 0.1, sorry. Yeah, that's my classical oscillator. 0.05 joules. 0.05 joules, that's the energy that I'm getting. And now the difficult part is this one here, is this next one. What's the quantum number associated with this energy level? Assuming that the frequency is correct, right? Quantum number associated with this energy. Okay, so what we end up having here, the quantum number must be equal to the classical mechanic energy, must be NHF equal, okay? That's the equation that we want to solve. Now I want to take this one out. I want to solve for N, right? We already know what's the frequency. We can use the classical frequency in the equation for the Planck's frequency, something like that. And then we solve for that. Plug in the numbers, 0.05, 0.05 times what? No, it's not times, it's divided by the frequency. The frequency is 5.03, and the quantum number. The quantum number is, let's take a look. You don't have to memorize, but you have to know that it's a very small number, 6.626 times 10 to minus 34. If you do dimensional analysis, you should get the correct result. Okay, so if what I'm getting here for the quantum number is a very large number. Do you see that? 1.5 times 10 to the 31 is a large number, extremely large number. 1.5. 1.5 times 10 to 31. Okay. We're going to do another, no? What would be the energy value for the next quantum number? What would be the energy value difference, right? Someone is coming here. For the next quantum number. No, wait a minute. What would be the energy? Yeah. What would be the energy value difference for the next quantum number? N plus 1. Okay. Okay, so we found, right? We found that E sub n, right, is 0.05 joules. So the question is like that. Basically, I'm asking the following question. What is En plus 1? What is En plus 1? That's what we are asking. Is it much different? What En plus 1 and En plus 1 minus En. What is En plus 1? And En plus 1 minus En. Okay, we can do that too. And you're going to see an important difference. Okay, here you go. We use this result right in here. I'm going to do better than that. Here you go. I'm going to use this one here. Okay, En plus 1 is going to be what? N plus 1 HF. Okay. Look what we're going to get. That's N. And that's 1. This number here is very small compared to this one. Okay. HF is going to be what? 0.05 divided by NF. N divided by that. By this integer number. Okay. In order for you to have a better grasp of the difference, look at that. One is very small compared to that. One is very small compared to that. So N plus 1 is almost the same as E sub N. I'm going to put it here. It's approximately equal to E. That's because that value of N, original value of N, is very small. That not very small, very large. Okay. So if you want to calculate delta N, right? Delta E. I'm gonna do that here. You go. Delta E N is equal to N plus 1 minus N, which, by the way, is going to be given by HF. HF. Go there to our Planck's constant. Planck's constant. Oh, I missed it, right? Oh, here you go. That's the one. HF. Put the H here. 10 to minus 34. Okay, that should be joules second times the frequency. The frequency was what? 5.03 hertz, right? Which is 1 divided by second. And what do we get? We find that the difference is so small, is on the order of 3.33. 3.33 times 10 to minus 33 joules. The energy is so small that we cannot measure with our instruments. The energy difference is so small that comes to be negligible compared to this value here. See, compare those two. So we can write it down like the following note. See that the energy that you add by going from one level to the next higher level is very small. It's negligible. It's negligible, negligible, and indistinguishable from the previous level. Okay, why? So what's the conclusion? Because of that, it is very hard to observe the next quantized energy level for classical objects. Okay. 10:30. Let's do another example. We are going to do something else now, more quantized level. In this example, the previous example, right, was for a classical oscillator. What for a quantum oscillator? Okay, that's the next example. Example. Let an electron of mass, remember the mass of the electron? It's a very small mass, right? 10 to minus 31 kilograms. Oscillating at a frequency of the red light. Red light is around 400 terahertz, which corresponds to 600 nanometers, a wavelength of roughly 600 nanometers. Fine. A. It's okay, corresponding spring constant, right? That's how we make analogies with the classical. We need to make an analogy with the classical mechanics to find the spring constant. It's corresponding mechanical energy according to the classical equation for an amplitude of oscillation that must be on the order of a nanometer, because that's the type of dimensions that we find for an atom. For an amplitude of oscillation, A equal to 0.5 nanometers, half of a nanometer. Okay. The next is, what is the corresponding quantum number n associated with the energy derived in B? Is this value acceptable? Is this value acceptable according to Planck's hypothesis? And then D, what are, right? What are the two closest energy levels for the value obtained in C. Okay, so this is an example. Let's put this one here, example 1, right? This is example 1. Here you go. The classical oscillator and its relation to the quantum oscillator. And now it's the contrary, right? The quantum oscillator and its relation to the quantum oscillator and its relation to the classical oscillator. That are those two examples are all about. One is the inverse of the other. We can come up with a solution. We're going to have our break very soon. Okay, A, spring constant. We are going to use the frequency equation to find out the corresponding spring constant. Right? We have that. We know that. That's visible wavelength. We want to find that. I'll put it in boldface. Okay. We're going to multiply by pi. Ooh. Here you go, pi. F. 2 pi f. This guy disappeared. We square both sides of the equation for okay, and then we solve for k. That's the one. That's the equation we want. Let's calculate that. Going back to my, okay, I know that this term here is around 40 because pi squared is around 10. That's a very good rule of thumb to do, right? But let's do that in the actual way. Pi squared, right? Times what? F squared. F squared is 400 terahertz. 400 terahertz. Oh, don't forget this thing has to be squared, right? And what's tera? Let's see. You know, we have terahertz. Terahertz. Terahertz is 10 to the 12. Okay. Tera, let's look at tera just to make sure. Tera. 10 to the 12 is a billion, right? Kilo is 1,000. Mega is a million. Giga is a billion. Hey, wait a minute, it's not a billion, this is a trillion. And the next one is tera. Okay, that's how it goes. I'm gonna write that down here for you. But before, let me put 10 to the 12 here. It's a billion, it's a trillion, not a billion. 1,000, a million, a billion, a trillion. And we still have to square this thing. Look here. Still have to square that. I still have to multiply by the mass of the electron, right? I didn't do that yet. Yep, gotta put it right in here. Let's take a look there. Yeah, I still have to put the mass of the electron. And the mass of the electron was given as 9.1 times 10 to minus 31. 9.1 times 10 to minus 31. Okay. So if this guy is big, right? If the square of this value is big, then this also is very big as well. Let's see what I get. I'm getting 5.74. 5.75 in the unit of K. 5.75, the unit of K, Newton per meter. Newton per meter. That's the spring constant of your electron that is oscillating at the frequency, at one of the frequencies in the visible. That's how we can model those electrons. The electric charge. Okay? Then we gotta know what's the corresponding mechanical energy. Let's take a look at the mechanical energy. He's asking for the mechanical energy, right? Not the quantum energy. B. Here you go. Now that we found K, and we have A, which by the way is half nanometer, we can find out what would be the corresponding energy according to the classical oscillator. Half K A square. A square is half 10 to minus 9. And don't forget to square it. That's what I'm getting for the mechanical energy. It's a very small value. Should be very difficult to measure that. I get 7.19 times 10 to minus 19 joules. Oh, gotta switch it. Okay. And let's see if Planck's assumption can accommodate this type of energy or not. Let's see. All right. Quantum. Here you go. That's classical. I'm going to put it classical model. Or even better, I'm going to put mechanics, right? Regular mechanics. And then I'm going to make this mechanical energy equal to Planck's energy. Planck's energy. Planck's assumption. NHF. Okay. Which is equal to that. Like that. My N would be HF. HF. HH, let's go get H. The frequency we have, terahertz, 400 terahertz, right? Here's 400 10 to the 12 hertz. And then we have to worry about this H, which again is a very small number. 6 point, what else? 6 point something, right? And I just copy and paste it somewhere else. Let's see, where is it? Look for it. Here you go. That's the value. 6.6626. Right in here. Joule seconds. 10 to minus 34. Okay. And now we can go ahead and plug it in our spreadsheet. We're going to have our break very soon, right? So go there. 7.19. 7.19. Put the equal sign here. 7.19. 10 to minus 19. To minus 19 divided by 6.62. 6.626 times 10 to minus 34. Minus 34. 400 times 400 times 10 to the 12, and then we close parentheses here. Look what we are getting. If I do the math, I'm getting, going back there, 2.71, right? 2.71. This is a result that we get from the classical theory, making the classical energy equal to the Planck energy. Okay, this number is not acceptable. Okay, the above number is not acceptable. The above number is not acceptable in terms of the Planck assumption, hypothesis. Because it must be an integer number. Okay, if we were to look at that drawing of the energy levels, here you go. Here's energy level n equal to 1. This is energy level n equal to 2 and 3. So only those energy levels here are allowed for that specific electron. And yet we are getting a result that is anywhere between 2 and 3, right? Okay. We're getting that because you are making a quantum energy equal to a classical mechanical energy. That's why you're getting that. Quantum doesn't allow, Planck's hypothesis doesn't allow. It's not acceptable for that. But we can calculate what would be the energy levels surrounding this value. What would be the energy level 2HF? What would be the energy level 3HF, right? That's what we're asking here in the fourth item. What are the two closest energy level for the value obtained in C? Okay, the two closest energy levels obtained above correspond to 2HF and 3HF. And then you go ahead, do the math, and you will be able to find out that those numbers, I'm not going to do the details here, otherwise, it's going to take too long, right? E Planck, E for n equal to 2, E2, is going to be 5.3 times 10 to minus 19 joules. Okay, that would be one. The other one, energy level at 3, okay, energy level at 3 is going to be what? It's going to be 3 divided by 2, multiplied by that. Right? What are we doing? we are dividing the number 2 in this result by 2, right? And multiplying by 3, right? That's what it is, 3HF, right? That's what 3HF is all about. This one is, you go, 2HF, okay? So multiply by 3, divide by 2, and you get this energy level here that you see here. And if you do your math, you're going to get something almost equal to 7.95 times 10 to the minus 19 joules. Okay? We can go also to HF, but we can stop here. HF, you know, the first energy level would be half of this value, which would be around 2.65 10 to the minus 19, right? Let's write it down. The first energy level of my electron, the lowest possible level of the electron, right, would be this value divided by 2. He didn't ask for that, but we are doing that anyway. 2.65 times 10 to the minus 19. So very important. Einstein was paying attention to this theory developed by Max Planck. Max Planck didn't give much credit for his own work, okay? He thought that what he did was just a type of phenomenological approach of an experimental result. It was like a theory fitting the data, right? You know the experimental result, what it is, and he starts thinking, how can I come up with a theory that would explain that data, right? That a phenomenological theory. And he came up with this quantum hypothesis. All he had to do was to find the value of that multiplicative term that you have here. And he published the paper, moved on. He didn't give much credit for his work. That's historically what happens, right? That the TV series, they emphasize that. Einstein approaches Max Planck, very excited about his result. Einstein, Mr. Planck, your result is amazing because I have been using the same procedure for another type of phenomenon that we haven't been able to explain for the past 50 years. And by using the constant, that's what Einstein told Max Planck, by using the constant that you derived in your black body problem, I was able to explain the photoelectric effect. The same photoelectric effect that Heinrich Hertz discovered when he was performing his experiments on electromagnetic waves around 1850. Okay, I believe we discussed that here. That story on Hertz and electromagnetic waves, you know, they are all connected with one another. And Max Planck still didn't believe that his theory was something important. But Einstein said, no, it's very important what you're doing. Don't give up. You know, it's a major shift in what we understand as being the physics. That's what Einstein, the younger man, talking to the older man. Okay? And everything starts with the black body radiation. And what we're going to talk next, after the break, of course, right? Break. We went too far, right? 10:55 a.m. to 11:05 a.m. is the photoelectric effect that was a contribution by Einstein, okay? Next, the photoelectric effect. And by the way, we have solar panels, we have solar energy today because of this effect. There is no coincidence that we study it. Okay, I installed 14 solar panels here in my home in Brazil, and it's generating electricity, and that's because of the photoelectric effect. Okay, any questions about that? Did I miss any messages from you? Hopefully not. And but there's no questions. Oh, it's 11:10, right? Not 11:05, 11:10 a.m. There is one more student, right, that just joined us. It is Zaid. Zaid, are you there? Okay, thank you. So I'm gonna give you attendance, okay, for that. And I see you folks in 15 minutes. Okay, we're back here. So remember the summary that we have here. Okay, that's the whole story. That's the that what happened. The important contribution was this one here, the energy levels of the oscillator, of the quantum oscillator, are quantized or discrete. Unlike that important difference, but just the energy, right? Whereas the classical oscillator is not quantized. It is written in terms of continuous values. We can even, we can even reinstate this. Let's say we can even here write this equation in terms of the frequency, okay? So we can compare the two ones here. Let's see how it looks like in terms of the frequency. The spring constant has a relationship with the frequency. Let's take a look. K, where is K? Yeah, we gotta get from this result here, right? Let's see if we have a better equation so we don't have to. Oh yeah, we did. We do. We derived that. So if you were to write the classical oscillator in terms of the frequency alone, we would write in this way. We still notice that the frequency here is squared, right? It's not a linear relation. This equation that you see here is the same as this one here, just written in terms of the frequency. And we should have a square term in there. But now let's talk about the photoelectric effect. The photoelectric effect. Let's take a look right here. Photoelectric effect. Wikipedia, let's take a look at the Wikipedia. Right? We go and let's take a look at the history of photoelectric effect. History, 19th century. Well, it was not Hendrik Hertz who discovered the photoelectric effect. It was Becquerel, Alexander Edmond Becquerel. He was a chemist. Well, they call it a physicist, but at that time, physics and chemistry was not much different, right? So much that Marie Curie, right? Marie Curie, she won a Nobel Prize in physics and another one in chemistry. So Becquerel discovered the photoelectric effect while studying the effect of electrolytic cells. Electrolytic cells is just what we use for a battery, though not equivalent to the photoelectric effect, okay? Electrolytic cells is not equivalent to the photoelectric effect. His work on photovoltaics was instrumental in showing a strong relationship between light and electronic properties of materials. Okay, in 1873, discovered conductivity in selenium, and oh, here you go, 1887, Henry Hertz. Okay, so 1839, and one of the incredible contributions of Henry Hertz, observed the photoelectric effect and reported on the production and reception of electromagnetic waves. What's the difference between Henry Hertz and the other guys? The effect of light on electrolytic cells was instrumental in showing a strong relationship between light and electronic properties. Okay, 1873 will be, so it was kind of an indirect discovery of the photoelectric effect. Now this guy discovered photoconductivity in selenium while testing this metal, the metal for its high resistance property. John Elster and Hans Gittel, students in Heidelberg, investigate the effect produced by light on an electrified bodies and developed the first practical photoelectric cells that could be used to measure the intensity of the light. Okay, that's very important. That's very important. So they invented the first photodetector. They arranged metals with respect to their power of discharging negative electricity. People usually give credit to Hertz, but to discovering the photoelectric effect. But he actually, all those people who preceded him has some credit on that. They arranged metals with respect to their power of discharging negative electricity. Very important. Okay. Rubidium, potassium, alloy of potassium and sodium. This guy made experiments with all sorts of metals to discover, to produce a photo cell. Okay, photoelectric cell. What is a photocell, right? And what is the photoelectric effect, too? You have to understand first what the photoelectric effect is. Okay, so let me introduce you here. Suppose that you have a metal, okay? That the discovery was done with metals. Nowadays, we use materials that are not metal necessarily. But, those metals have electrons there. They have free electrons. That's what metals have. The valence electrons in metals are the ones that are kind of free electrons. They're not bound. They're not tightly bound to the atoms. Can you picture that? When you bunch together a bunch of, when you put together a bunch of atoms, a bunch of metallic atoms, just like iron, for instance, you create the sea of electrons that are almost free. The valence, those free electrons are the valence electrons that they can move back and forth. They're not tightly bound to the atom. Okay. And what people discovered, and Hertz, especially Hertz, right? He observed that when he shone UV light onto a metal, he observed a phenomenon that would give the interpretation to him that some of the electrons would be ejected from this metal. That's what he observed in his electromagnetic experiments. Shine UV light, and some electrons would pop out from the atom. People couldn't quite understand why that happens, especially with classical mechanics. Okay, here's the electron, UV light, and depending on the wavelength of the UV light, you'd get a faster electron, a slower electron, and so on. That's what the photoelectric effect is all about. Okay, and in the case of solar cells, light from the sun produces a current. It's somewhat related to the photoelectric effect. It's not exactly the same. Okay, and the explanation goes according to the valence electrons. Here's the model of the atom. with the valence electrons. And the nucleus. Valence electrons and the more tightly bound electrons that are close to the nucleus. The inner electrons. Okay. When you put those metals one next to another one, just like in a bar of iron, a bar of steel, you have all those atoms brought closer together. If the valence electrons are lightly bounded, when you put all those atoms together, something else happens. Those electrons, those lightly bounded electrons, those valence electrons, they can move from one atom to another. They're so far away from the nucleus of the atom that they can move from one atom to another, producing this sea of electrons, a sea of flowing electrons. That's the idea. That's the model that you have to have in your mind, okay? If those electrons are the surface of a metal, it's possible to eject them by giving one small bit of energy. This small bit of energy is called the work function of the metal. Metals have different work functions. Depending on the metal, you require more or less energy. That's why that guy that you saw was working with different metals. Okay, they arranged metals with respect to their power of discharging negative electricity. John Elster and Hans Gittel. Okay, Heidelberg is a city in Germany. So they came up with this table, right? So they can say what they could state which one was easier to discharge the electrons, which one was more difficult. And that was very close, that those experiments were very close to Volta's experiment, Alexander Volta. And what you see here has to do with what we call the work function. Let's take a look at the work function. Hopefully, let's see, work function we may have something like that here, work function. Yeah, work function. Okay. Each metal has its own work function, and we should be able to find a table. If it's not here, it's going to be elsewhere. Right? Work function, work function, work function for a given metal. Let's take a look. Work function of metals. Work functions of metals. Let's see, they have a table here. The work function is just a measure of how much energy you need to give an atom to eject an electron. Okay, this one, I don't think they have it. It's going to be a little bit difficult to find something here. Let's see, table, work function table. Yeah, okay, Wikipedia again, right? Let's see if we have work function. Okay, right in here. Of elements, silver, gold, they're atoms, they are metals, right? Beryllium, okay, and so on. Calcium, cobalt, copper. Take a look at the value of work functions. And those values are given in terms of electron volts, not joules, but electron volts. There is a relationship between joules and electron volts, okay? They vary on the order of 3, 4 electron volts. That's not difficult to memorize that, right? 3, 4, 5, 6. Oh, there is one that's 2.7, another one that's below 2. Oh, another one below 3, right? anywhere between 2.2, right, and 6. 2.2 and 6. The highest one I see here is 5.93. So it's fair to say that the work function of metals is anywhere between 2 and 6 electron volts. Remember, electron volts, then you have to change that to joules. You have to change that to joules, right? So that's very easy to memorize, right? The one that has a higher work function requires more energy to eject the electron. Here's the plutonium. It's not plutonium, platinum. Very noble metal. Do we have plutonium here now? We don't have. AgAuB, cobalt, gallium, mercury, potassium. What's this one here? Lutetium. Oh. Molybdenum. Neodymium. Yep. This one is plumb. Plumb is lead. Okay. Plumb in Latin. Rubidium. This one is ruthenium, and so on, right? Titanium, right? This one should be titanium. Yep. Titanium, vanadium. Yep. Vanadium, ytterbium, zinc. Which one is this one here? Tungsten. This one is tungsten. Tungsten is W. Thallium, and so on. Oh, uranium right in here. Okay, so keep that in mind. What is the work function of metals? Next, the photoelectric effect. Okay, back in the 1800s, scientists discovered that light could eject electrons from the surface of metals. The amount of ejected electrons depended on the type of metal and is related to their work function. So what is work function? What is work function? Okay, WF, right, is the energy required to eject electrons. The minimum energy is the minimum energy required to eject electrons from metal. Its value is somewhere between 2 and 6 electron volts, depending on the metal, okay? If you want to have an idea what 1 electron volt is, let's just take a look here in Wikipedia, in the internet, right? Electron, EV, EV and joules, right? EV and joules. Okay, that's the conversion between one and another. 1 electron volts is 1.6 times 10 to minus 19 joules. Do you recognize this number here? Memorize it quickly, and I'm going to show you, charge of electrons, of the electron, right? What's the charge of the electron? elementary charge. Take a look at this number here. That's the charge of the electron. 1.6 times 10 to minus 19 coulombs. 1.6218 times 10 to minus 19 joules. Okay? So 1 electron volt, okay? 1 electron volt is nothing but 1 times the elementary charge times volts. That's what it is. Volts, what's the unit of volts? Volts is joule per charge, right? So when you multiply the electric charge by the voltage, you get something, you get a unit of energy. So 1 electron volt is going to be 6 point what? 1.6. 1.6 times 10 to minus 19 coulombs volts. Like that. That's how we get, which, by the way, simple enough, right? Electron volts is exactly what the name implies. Is the unit of charge of the electron, is the charge of the electron multiplied by volts. So that's what people observe. But that was not the problem. Okay, that was not the problem. Classical mechanics, you know, classical mechanics, and by classical mechanics, I mean electromagnetic theory, right? Did predict that electromagnetic waves carried some energy with them. Consequently, it was rather natural that the energy of an electromagnetic wave could be used to eject an electron from the surface of a metal. Quite natural. There's no problem here. The problem was in the details. The problem was in the details. Classical theory did predict that, yes, I shine a light in the metal, and the metal has enough, and the light has enough energy to eject an electron from the metal. That's not a problem. Scientists were not debating that. The theory, at least in a qualitative sense, would predict something like that. The problem was in the details. The problem was in the quantitative behavior of what they were observed. Okay, that was the problem. Qualitatively speaking, it was rather acceptable that classical theory could impart energy to the atoms in a metal and eject their electrons. Okay? Impart energy to electrons, right? To electrons in an atom and eject them. Eject them from metal surface. Qualitatively, that was not a dispute. Qualitatively speaking, Mama, that was not the dispute. The dispute was in the quantitative behavior. The dispute were in the details. Okay? That was the dispute. And that's where classical theory was breaking down. And that's where classical theory was breaking down. Just like it broke down as relativity theory, just like it broke down with the Maxwell-Morley experiment, just like it broke down with the black body radiation. Okay? That is where classical theory was breaking down. In other words, right? In other words, details. Okay, so one important experimental result. One important experimental result. Okay? Scientists, according to classical theory, okay? According to classical theory, if you increase the intensity of the light, the light intensity, you'll be able to eject more electrons. But that was not what that was not what was being observed. Instead, you had to increase the frequency of the light or decrease its wavelengths. That's what they were observing. More electrons, in other words, more electrons would be ejected only if you increased the frequency of the electromagnetic wave, not its intensity. And they start thinking, what's going on here, right? And that's what Henry Hertz was observing in his experiment. They even mentioned it here, right? History. Heinrich Hertz observed the photoelectric effect and reported on the production and reception of the electromagnetic waves. They're completely different phenomena, right? But he did observe the photoelectric effect while he was performing his electromagnetic waves, his classical electromagnetic waves experiment. The receiver, look here, the receiver in his apparatus consists of a coil with a spark gap. That's the type of antenna that Hertz had at the time. Okay, it was a gap surrounded by two metals. They're not touching each other, in close contact with each metals. A gap between two metals, okay? Not in contact, but a gap between two metals. Okay, and when he had his electromagnetic wave produced, you'd see a spark jumping from one end of the metal to the other one. Okay? And that, he concluded, was due to the electromagnetic waves that he was producing far away, 5 meters away. That's what he concluded. Though that spark that he was observing was due to the electromagnetic waves that he was producing 5 meters away there in his laboratory. So in order to see those sparks better, right, more clearly, what he did, he placed the apparatus in a darkened box to see the spark better. We do that even today. If you want to measure light You want to isolate your detector from the ambient light. And then what do? You put that inside a darkened box. When I was doing some consulting for a company there in Cadoga Park, the guy, the president of the company, did the same thing that we are saying here. We want to detect some light with our detector. He got his box, this cardboard box, okay? Big company, and he had his cardboard box there, put his detector there inside, so there's no light in, and that's exactly what Hertz did as well. Okay, however, he noticed that the maximum spark length was reduced when inside the box. What the spark length? It means that the two metal contacts were further apart. Okay. And then it looks like the darkened box was insulating the antenna from the transmitter. That's what it looks like. A glass panel placed between the source of electromagnetic waves and the receiver absorbed ultraviolet radiation that assisted the electrons in jumping across the gap. Okay? So he go ahead, and today we know that, right? If you want to filter electromagnetic radiation, you use a glass, you use plastic. They block, those materials, they block ultraviolet radiation. So that's the experiment he performed. He put a glass panel, okay? And the spark across the gap decreased. He removed the glass panel and the spark length would increase. What do we mean again? Let me explain what do I mean by spark length, right? Spark length means the distance between the two metals, the gap between the two metals, okay? It's just like you approaching your hand, you're electrically charged, and you approach your hand to the knob of your door. The closer you are, it's easier for you to discharge, right? But there is this maximum distance in which you still get a discharge. So that's what Hertz was doing. He was increasing and decreasing this gap, okay? And he wanted to know what was the longest length of the gap that he could see a spark jumping from one electrode to the other one. With the glass panel, this distance was smaller. Without the glass panel, this distance was larger. Okay? When the glass panel was removed, the spark length increased. He observed no decrease in spark length. Oh, he observed no decrease in spark length when he replaced the glass with quartz. Quartz is a different type of glass. Quartz is a different type of glass. We know that quartz does not absorb UV radiation. Okay? And what would be Hertz's surprise if he were to shine UV light in that gap? Okay. What they discovered by Hertz led to a series of investigation by Hawax, Hoare, Riggs, Stoletov on the effect of light, and especially of ultraviolet light on charged bodies. Hawax connected zinc plate to electroscope. He allowed ultraviolet light to fall on a freshly cleaned zinc plate and observed that zinc plate became uncharged if initially negatively charged. Look, imagine the experiment. It's a very simple experiment. You get this zinc plate, charge the zinc plate, shine ultraviolet light, and he would observe that the charge in the zinc plate would decrease. Okay? Positively charged if initially uncharged, and more positively charged if initially positively charged. So the metal was getting rid, the UV light was getting rid of the negative charges. That's what he was observing. From this observation, think about that, folks. Today we discussed the thing in only half an hour or 1 hour, right? But those experiments had to be performed throughout several days, months, and years until someone figured out what's happening, okay? And those are the results that they are getting. From this observation, he concluded that some negatively charged particles were emitted by the zinc plate when exposed to UV light. That is the photoelectric effect. With regards to the Hertz effect, the researchers from the start showed the complexity of the phenomenon of photoelectric fatigue. the progressive diminution of effect observed upon fresh metallic surfaces. Okay, but the important thing that you have to know is this last phrase here, ultraviolet light. It had to do with the frequency of the light. It didn't have to do with the intensity of the light. And the scientists of the time couldn't explain that. How come it's a function of the wavelength of the light and not of the intensity of the light? That's what classical mechanics was predicting, right? Well, and then came Einstein, okay? Einstein came up with that important contribution that we use even today. This contribution was cited by the Nobel Prize committee. They didn't cite the contribution that Einstein made to special relativity because at the time nobody would understand special relativity. Einstein was just one of the few that would understand special relativity, but they still had to give a Nobel Prize to Einstein because he made other contributions. He made contributions on the photoelectric effect. He made contributions on the Brownian motions of molecules. And that was cited by the committee. And other contributions. That's what the Nobel Prize committee cited. Okay? And we can even see, here you go, there is a website for the Nobel Prize website that listed all the winners there and what was cited, right? Well, Nobel Prize, okay, here you go. No, that's not this one. Here you go, nobelprize.org. Nobelprize.org, that's the actual site. Nobel Prize laureates, all Nobel Prize, Physics Prize. And there is about the prize, how to, latest, that's the latest one, 2022, right? That's the new physics. And how many physics laureates can you match? Here you go. The Nobel Prize categories. Well, Albert Einstein, here you go. For his services to theoretical physics, and especially the discovery of the law of the photoelectric effect. They didn't mention the special theory of relativity. Nobel Prize in Physics 1921. Okay. Life, work, right? Nobel Prize. That's for his service to theoretical physics, right? The special relativity is already here in the theoretical physics, and especially the law of the photoelectric effect, and that's what we are going to talk about. Okay, so what was Einstein's contribution? Hearing about the Planck's contribution, right? The Planck's hypothesis. Einstein hypothesized that the energy of the light had nothing to do with the intensity of the light, but it had to do with the frequency of the light. And then that's what he used, right? He used the Planck's hypothesis in his own photoelectric effect. If we were to rewrite that in terms of the wavelengths, that's what made Einstein so excited about the discovery of about the theory, right? Planck's theory, Planck's hypothesis, is that he could explain the photoelectric effect in terms of the wavelengths if he applied Planck's hypothesis. And the mechanical energy of the photon was given by this formula that was directly related to the frequency of the atom. So the higher the frequency, the more energy the light is imparting to the electron. Okay, actually it's not N here, N is for the Planck, right? Let me correct myself. It's just HF. NHF is the theory of Planck. Planck's theory, right? Let's write it down. Planck's Siri, assume that the quantum oscillator, in this case was the electron, had energy levels given by, here we go, remember that. But now Einstein made the connection between the frequency of oscillation of the quantum oscillator and the wavelengths of the light. So here we have each photon had this energy, each photon, which written in terms, okay, Einstein hypothesized that each photon of light had an energy given by the Planck's formula. Okay, here's the energy of the quantum oscillator. I'm going to emphasize quantum oscillator. Here's the energy of each photon of light. But now the frequency of the photon is different than the frequency of the oscillator, right? Here's the frequency of a oscillator. Here's the frequency of a wave. Energy, and I'm going to put here, light was made of corpuscles of light that we call the photon. And now we can start looking at the energy of each photon of light of different frequencies and wavelengths. And that was one of the examples that I have, example 1. Okay. One photon has a frequency of 400 terahertz. By the way, that's the red light. What is its energy according to Einstein? And then we can come up with a solution. We're going to go in the break very soon. We go ahead, multiply, h by this frequency, and then what we get, we're going to get something like 2.65 times 10 to minus 19 joules. Okay. Let's take a look. Remember the electron volt, the value of the electron volt, and the value of the electric charge, right? Let's take a look at the electron volt. Here you go. 1 electron volt is 1.6 times 10 to minus 19 joules. Okay, so this is a little bit more than 1 electron volt. Okay, how many electron volts that is divide 2.65 by 1.19, 1.6, 2.65 by 1.6, 2.65 by 1.6, and we get what? 165 electron volts. This is equal to 1.65 electron volts. Is it enough to eject an electron from a metal surface? Right? Let's see. Is it enough? It's below 2 electron volts. Red light cannot do that. Red light cannot do that. See that? Okay. And what was the explanation that Einstein gave to this photoelectric effect? Okay. Explanation was that the light, the photon behaved like a point particle that was colliding with the electron. Not a wave that was imparting an energy little by little by the electron, but it's a momentaneous collision between the photon, a photon of light and an electron. Okay, so here we go. We can do the same for UV light if you want. Okay. What was the process of production of photoelectrons? So those electrons that are emitted, we call the photoelectrons. Instead of imparting energy little by little to the electron, the photon of light would collide with the electron, emitting the electron almost instantaneously. There was no time frame between you shine the light and getting the photon, the electron emitted. Okay, so that's what you have for that's the basic idea of the photoelectric effect. That's the basic idea of the photoelectric effect, okay? So going back to our work function, admit, now that you have an idea of the energy of a red light is around 1.5, 1.6, right? Of a quantum of red light, 1.6 electron volt, which is below the minimum energy here in this table. If you were, instead of using blue light, that is around 400 nanometers and closer to UV light, 400 or 600 is 1.5 times more, right? That's less than the red light. Let's take a look. Here you go. Blue light has a wavelength of 400. Red light has a wavelength of 600, approximately. Now we have blue light has 1.5 times more energy than your red light. Going back here to our nodes, 1.65 multiplied by 1.5. Okay, now we start getting within the range of the work function of metals, 2.447, 2.5 approximately. Now, and if we go into the UV wavelengths, which is around 300 nanometers, now you are talking about energies on the order of 3.3 electron volts. 300 nanometers is the range of UV, of the UV wavelengths. So just by moving from the red light to UV light, you have twice as much energy that can be used to eject an electron from the surface of a metal, okay? That's the idea, and we are coming to a point that we are going to have our break again, and now our lunch break. Okay. In the UV wavelengths, in the UV range, this energy is at least twice the above, which already falls within the range of the work function of many metals, a 3.2 Okay, any questions? Anybody came in that was not called? Let's see. Okay, let's go ahead and have our break, 12 noon until 12:30, right? 12:30 p.m. When we return, we will have our lab. Okay? So see you in half an hour. I'm back here. The next lab is going to be the speed of sound lab. So the order is a little bit different compared to that what you saw in the lab manual, in case you bought lab manual, right? And notes. So insert, page break, lab 5. That's the one we're going to do, the speed of the sound lab. Okay. Okay, so here we go. We have that. Let me see if I have one more here. No, that's okay. Let's go back to that, and I need to upload your spreadsheets. I believe it must be this one here. Okay, no, it's not this one. Maybe it's this one. Yeah, that's the one. Okay. This is a very interesting experiment. Unfortunately, we are not doing the actual experiment. It works very well. I'm gonna change. Okay, okay, this one should be L505. Let's take a look at the syllabus. Sharing the screen, right? Can you see the screen here? I'm gonna scroll up and down. Just give me some feedback that you can see the screen being scrolled up and down. That's how I was scheduled. Yes, just say good. Thank you. Today is July 10th. That's what we're doing here. Matter waves 1 and the speed of sound experiment. Today, do on the 13th. 13th is when? Thursday. Yeah. Yeah, I'm giving until the exam to do this, but don't forget, that's final exam includes the lab as well. Final, let's see, 3, 4, 4. I'll get that later. And I'm going to upload those labs for you. Group 1, Group 2, Group 3, Group 4, Group 5. You should have your spreadsheet there. So download the spreadsheet for lab 5 for your group folder. Let's see what's going on here. No, that doesn't apply, right? I corrected so far only labs 1 and 2, right? Yeah, only lab 1 and 2. So I'll be correcting whatever is I'll be correcting whatever is pending today. And so check your group folder later on. Please check your group folder. Please check your group folder later on. Okay, so what this lab is all about? This lab is about measuring the speed of sound. And we do this experiment by using a technique that we call time of flight experiment. Okay, well, what's time of flight? It is time of flight of the sound wave. Okay, sound wave. The sound travels very fast. So this is not because the sound travels very fast. Okay, sound travels very fast, and by fast I mean 330 meters per second. We cannot use the human senses, right, to determine its speed. We have to use something else. We have to use, cannot use let's put it this way, cannot use a regular timepiece, let's put it this way, it's better, to determine its speed. We have to use different type of timepiece. And there's going to be a difference between quotes. We must use a different type of timepiece. One way to do that would be to set a speaker very far away, if you want to do, right? If you want to do that the regular timepiece, you have to set a speaker very far away from you, 1 kilometer away from you, for instance. Have someone operate the speaker and give you a hand signal when he turns on the speaker, or turn on a light, right? Turn on a light and shine the light towards you. Then you keep on paying attention when the sound is going to arrive your ear. That's one way. So the moment that the guy gives a hand signal, right, you start your timer. And then keep on listening to the sound. Once you hear it, you stop your timer. That would be one way of performing the experiment. That would be one way of performing the experiment. But we do not have 1 kilometer length distance. And for 1 kilometer distance, also your sound, your speaker must be a very loud one. Otherwise, you won't be able to hear it. So we do it in a different way. That would be, what I did here, is a time of flight experiment. You start the timer to determine how long it takes for the sound to fly from one place to your ear. That's a place that's a kilometer away. That would be a time of flight experiment. But we don't have 1 kilometer distance to do that. Instead, we do something else. Instead, we use a shorter distance. Let's see, put like that. Unfortunately, it would be very cumbersome to perform this experiment by setting a source that is 1 kilometer away from you. Okay. Not only would it be cumbersome, not only it would be cumbersome, but the intensity of the sound decreases with the distance, and you may not be able to hear the signal that you are timing. Okay? Not only the distance is too far away, 1 kilometer, who is going to set up a lab in a lab experiment that one of the equipment is 1 kilometer away, right? But on the top of that, the intensity of the sound would decay. And you might not be able to hear the sound. Not just because the intensity of the sound is going to decay, not just because the intensity of the sound is going to decay, but on the top of that, you have to handle all sorts of noise that comes elsewhere that would mask your sound. Okay, so that's not feasible, that's not realistic. But at least you have an idea how you can do this experiment, how you can measure the time of flight of a sound wave. Okay. Instead, we use a shorter distance and some sophisticated equipment. The experiment that we perform in the classroom, we are dealing in this experiment, in the classroom experiment, we are dealing with distances on the order of 1 meter at most. Think about that. Think about that, how long it takes the sound to travel 1 meter. We can do the math, right? Let's do the math. Let's do the math. Let us come up with an estimate. What would be the time of flight for the sound to displace 1 meter? right? The calculation goes like that. We do know that the sound displays 330 meters in a single second. We know that. We want to know how long it takes for the sound to displace 1 meter. That's a simple rule of 3, right? And then you're going to see that the time is really short. Meter cancel with liter, right? The x go to the other side. 300 goes downstairs. And that how many seconds it takes for the sound to reach your device, but just for 1 meter length, okay? You cannot time it with your time piece. 1 divided by 330. We are talking about 3,000ths of a second. 3,000ths of a second to move from one place, from the speaker to the detector system of the sound. And the detector system of the sound is nothing but a microphone. So microphones are detectors of sound. Speakers are source of sound, okay? 0.003. It should take 0.003 seconds, 3,000ths of a second. I would say milliseconds, 3 milliseconds. Unfortunately, we cannot measure something like that with a regular timepiece. Okay. Even in those Formula One races, the timepieces that they use are on the order of, has a resolution of 1 millisecond. Even for timepieces used in Formula One race, that would be difficult to measure that. So you cannot do that with your senses. You have to have some sophisticated equipment. Okay. So how do we do that? And let's not forget, speaker, source of the sound. And by the way, microphone is a sound detector. The microphone can be used as a sound detector if it hooked up to a proper place, to a proper another instrument. Okay, so here you go. To measure the speed, the speed of the sound. Better, right? The speed of the sound. You need a sound source, a speaker. And what else? I'm going to, here you go. Here's the speaker. Speaker positioned at a table, okay? But you need something else too. Must be connected to a device that controls how the sound is generated. It's possible to do that with a device called, it's possible to do that with a device called the function generator. And that's exactly what the name says, is the device generates a function that goes in the form of an electrical signal, and this function controls your speaker. For instance, function generators out there can generate either sine waves, square waves, or triangular waves. Okay? Function generators available in the market, okay? Function generators available in the market can generate different types of functions in terms of an electrical signal. But by electrical signal means a voltage. What a voltage, okay? The voltage can be in a sinusoidal fashion, sinusoidal form, in a square form, or in a triangular form. Okay? Like that. Here you go. You can do that. With a device called the function generator. Every laboratory has a function generator. Okay? Let me see here. We say that the function generator in this experiment derives the speaker. Function generators are available in the market to generate different types of functions, different types of electrical signal functions or voltage, right? Functions. The voltage can be sinusoidal, can be a square. We say there's a square wave, can be a sinusoidal wave, right? A square wave. Square wave, instead of form, we put or a triangular wave. Let me show you one of those function generators that we have out there in the market. Function generator, here you go. Here you go. Different types of function generators. They are quoted here in Brazilian reais. You divide this number by 5 and you get it in dollars. Okay, something around $60, this one. Signals, digital signal generator. Okay, generator sine wave, arbitrary waveform. Ah, they have a arbitrary waveform frequency generator. Okay, so sine waves, square waves, triangular wave. Oh, they can generate a pulse wave as well. This one. In general, just those three. The function generators that we have there at Lay Harbor, just sine, square, and triangle wave, regular waves. And then there are others too. That this one looks like this one is more advanced than what we have. Okay, so if you put a multimeter to measure the output of this device, you would be able to see the signal, the voltage varying as time goes by. And then you have those knobs, okay? Wave output, see that? We can output the signal to our speaker, for instance. Can output the speaker to this. Can use this output to drive the speaker. Let's see if we can get a function generator connected. Let's see, speaker connected to a function generator. Let's see if we can find the YouTube, a YouTube video. It's much nicer if you can do this experiment on real, in real life, because you can play with it. Let's see here. Skip. Okay.
So this is a signal generator, and I have.
So this is a signal generator. You put the signal generator to 1,000, 1,000,000 kilohertz. That's a lot. Let's see what's going on. It's a sine wave, and here's the speaker. See the output, just like that device is shown here. Output. He's using this cable right here. Connect to the speaker. Oh, do you see here the sine wave? Sine wave, square, ramp, pulse. Then you can generate noise with this guy as well. Arbitrary and counts. There's in general, what we have there at the Lay Harbor is just those three. I've never seen those there at the LA Harbor. So the output is this one. The speaker is connected to the signal generator.
I have here a speaker. It's kind of dark. I had to make it darker because the screen would not be visible. Okay, and when I press this output button,
Okay, do you hear? That's the sound it's produced at this frequency. That's 1 million kilohertz. That's kind of crazy. No, it should yeah, it cannot be 1 hertz. It must be 1 kilohertz. Let's see what he said.
you hear this 1000 hertz, that is 1 kilohertz.
Okay, it's 1 kilohertz, just 1,000 hertz. Okay, human hearing sensitivity is between 20 hertz and 20,000 kilohertz. So we can hear this one, 1,000 hertz.
Frequency sound. Okay, and let's see. Or let's jump into the subject. So it's 1 kilohertz in frequency. And if I go a little bit to the right,
What he's going to do now, it looks like he's going to change the frequency, okay?
I can modify the frequency.
Yeah, here you go.
Down.
See, he's modifying this frequency. Yeah. 8.
Or up.
Okay. See, do you see the tone? The tone is different, right? Depending on the frequency, you hear a different tone. Okay.
Yeah.
Bass, right? That's bass. And that's 200 hertz.
So that's the frequency, and let's see that.
You can go lower until 20 and still might be able to hear. We may or may not, sometimes depend on your hearing sensitivity. The lowest frequency, in general, the average is 20 hertz. He's still at 200 hertz.
This is the voltage.
The voltage means the amplitude of the signal. The higher the voltage, the higher the amplitude of the signal.
5 volts peak to peak. If I increase the volume, I mean the voltage.
Yeah, he's increasing the amplitude.
Which
See
is
that?
the audio level of volume.
The tone remains the same, but the loudness or the intensity of the sound increases. Peak to peak. It's a sine wave. Don't forget this sine wave. Peak to peak means from the bottom to the top, right? From the valley to the crest. So the amplitude is actually 10 volts.
Yeah, that's not too loud. And we can play it further.
Do you see that we have a USB connection here in this guy? Nowadays, there are manufacturing function generators that have a USB port. In the past, we didn't have USB cables or connectors, right? Those function generators consequently didn't have a USB port, but now they're starting selling that. So you can now interface this device to a computer.
Around with the frequencies.
Frequency, 800 hertz.
Now, for example, it's set to sine wave. Let's make it a square wave.
Okay, now there's a square wave. That's how it here. That's how it sounds like.
Whoa, that's
See the difference?
Okay.
The sine wave is the more pure wave, is the one that sends a sound with a frequency exactly equal to 800 hertz. The square wave has some components that are outside 800 hertz, but it's around, okay? And then we have this other one, similar to another.
Pulse. Okay. Let's make a low note, 440 and hertz.
Okay, 440 hertz.
Amplitude.
Increasing the amplitude.
Okay. Let's see. That's
Okay, good. He's going down 100 hertz. That's what this driver does. That's what this function generator does. It drives the speaker.
Okay.
That's it. Oh, now it's coming out of the range of the human hearing. Okay, 50 hertz. Remember, this is a square wave. Okay. Now, look what's happening, all right? It's tick, 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 right? It's sending a pulse with this frequency, 1 hertz. And now you can. What it's doing here is increasing the frequency of this square wave.
It sounds like the test drive, big game.
A test drive for him.
Engine, the car engine, the test, something like that. Okay.
Okay. Okay, in our experiment, how do we do our experiment? In our experiment, we set the speaker to a square wave. We know that it works this way. Okay, let's move forward, right? Otherwise, it's not. Okay, so we set our speaker to be driven by square wave in our experiment. Okay. Square, 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 right? It's a square wave. You have that loud sound after a certain interval of time and then drops to 0. Loud sound drops to 0. Loud sound drops to 0. And that's done at a given frequency. And then on the top of that, we need a detector, a sophisticated detector. The human here cannot be used in this experiment. And this sophisticated detector is going to be a microphone. And this microphone has to be connected to oscilloscope. Oscilloscope, in case you don't know, oscilloscope. An oscilloscope is a fancy multimeter. Okay, this oscilloscope, the sound signal is connected by the collected by the microphone. The microphone transforms the sound into a electrical signal and input that electrical signal into the oscilloscope. So your oscilloscope is going to be your timepiece, by the way. That can also be used as a timepiece. A very fancy timepiece. And they are placed over a translation stage. Let's take a look here. Here you go. My speaker. This is a translation. The translation stage is this guy here. A translation stage over a little table. You can move it back and forth, okay, to make things, convenient. It's very important to have a good experimental setup so you can perform your experiments in a very convenient way. Here is your driver or the function generator that you saw how it works. And then here you go. Here's my microphone right in here. They are both set in a translation stage. This is a translation stage. This other one is a translation stage as well. Okay? And now they can be moved closer and further away in this little table that's more or less 1 meter distance. And then what do? We connect our microphone to my oscilloscope. Connect the microphone to my fancy multimeter or my fancy timepiece. Okay, this device has resolutions on the order of nanoseconds. Okay, let's take a look at oscilloscopes. Oscilloscope. What's the oscilloscope? Here you go. Never doing the oscilloscope. Let me see if I can get a better sound input. Wait, an oscilloscope. Let's try this one. Sound oscilloscope. Sounds on oscilloscope. Here you go. Okay, let's take a look at this one. So there are different pieces to this experiment, right? Do you see the microphone right here? That's the microphone. This microphone is connected to an oscilloscope.
Mary had a little lamb.
Do you see that? She's speaking here in the microphone, and the microphone is converting her sound signal into an electrical signal that's being picked up by the oscilloscope. If you put a frequency, if you put that speaker at a given frequency, like the guy was doing the other video, you would see a sinusoidal wave here.
Whose fleece was white as snow, and everywhere that Mary went, the lamb was sure to go.
Okay.
Mary had a little lamb, little lamb.
Okay.
Little lamb.
See, the waves is somewhat similar to that of a sine wave. Oh, here you go. This is the case of a tuning fork. This tuning fork emits sound waves at a specific frequency. If you come close enough, you might be able to read the frequency of this tuning fork. It seems like it is 879 hertz. The tuning fork, okay? And you can see clearly that we have a sine wave here, okay? And this oscilloscope can measure the frequency, right? Can measure the period of this wave. From the period of this wave, we get the frequency of the sound. The horizontal distance is seconds, okay? Oh, microseconds, see here? And in the vertical distance, we are measuring voltage. In this case, it's 50 millivolts. Okay, stop the tuning fork. What you see here is more like a beating wave, okay? So those are the two pieces of information that you must have in mind to understand how this experiment works. Okay, so going back here, an oscilloscope connected to, well, it's better a microphone connected to oscilloscope, okay? A microphone connected to an oscilloscope. Oscilloscope, the microphone changes the sound into an electric signal. Could be the voltage, right? And sends this information to the oscilloscope for display. Okay. The scales of the oscilloscope are the vertical direction, voltage, the voltage, and along the horizontal direction is time, instant of time. Okay. That's how it works. We'll place both the speaker and the microphone on a translation stage that can be moved back and forth on an optical bench. We call it optical bench. This one right in here, we can move this guy back and forth. Okay. And then what we're going to do? We are going to produce a sound wave here in this speaker that's gonna travel this distance until the microphone. Okay. And the microphone is gonna pick up the signal and display here in the oscilloscope. Remember, it's a square wave, but we're going to do something else too. The moment that this speaker emits the sound wave, which by the way is this guy here that's controlling the speaker, right? the function generator, right, is driving the speaker. And the moment that the function generator generates a square wave, it's gonna tell the oscilloscope, watch out, we already sent our sound. That's what this guy is telling the oscilloscope. Start your timepiece. Start your time device. Okay, that's what this guy is telling the oscilloscope. So they must be talking to each other. Okay, let's review again. Here you go. We start with a speaker connected to a function generator that's going to drive the speaker in a particular way, in a specific way. In this specific way is exactly a square wave. We know that square wave works well for this experiment. And the sound that's going to be emitted by the speaker is going to be picked up by a microphone connected to oscilloscope. It's not enough to connect those devices separately. It's not enough to connect this guy here separately from this one. Why is that? Because this oscilloscope must know when the sound is generated, so he can time how long it takes for the sound to travel from here to here. For this reason, we connect the function generator to the oscilloscope. Remember, this guy is traveling at the speed of the sound, but this signal here from the generator to oscilloscope is traveling at the speed of the light. It is an electromagnetic wave, far larger, 300,000 kilometers per second, on the order of 300,000 kilometers per second. Whereas the other one here is just 0.3 kilometers per second. It's 1,000,000 times faster, the signal here. So that's how it works. Here you go. I'm generating my signal. Start your timepiece, right? Start your timer. Here you go. Here's the wave propagating. The wave front propagating. Time t greater than 0 seconds. It's getting there. It's a square wave, so it should be, should be cut down somewhere. Okay. So it would be more reasonable if I were to delete this one here. Okay. So the wave is propagating until it reaches the microphone. I'm going to get the next slide. And this wave here has reached the microphone at this instant of time. Okay. And the moment that it reaches, you are going to see a signal more or less. It's not exactly this way, but it's going to be more or less this way here that you're seeing. Like that. Okay. The square wave traveling from this instant of time 0 to this instant of time, whatever. That's what my oscilloscope is measuring. This time of flight. Oscilloscopes can measure those short time intervals. Human ear cannot. Okay. So that's what you have to know about this experiment. That's a very qualitative idea of how it works. Okay, activate the speaker to generate the sound, and time is how long it takes for the sound to reach the microphone. You need a very special timepiece chronometer, right? Which is the oscilloscope. The microphone must be connected to the special timepiece. Suppose you have a distance x from the microphone to the speaker that you can measure with a ruler. Also, suppose that you manage to measure a time interval t for the sound to move this distance. Consequently, the speed of the sound will be x divided by t. Okay. So here's the list of equipment: speaker controller, which is the function generator, microphone, the timepiece is the oscilloscope, a means to control the distance of the microphone to the speaker, a graduated rail, which is my optical bench. Graduated rail or bench. Huh? We call it optical bench too because we use that for optical experiments. In this case, it's not an optical experiment. It's more like a sound experiment. You must get the speaker controller to talk to the timepiece. All right. the function, the speaker controller / function generator, talk to the timepiece, 2 translation stages, one for the speaker, another one for the microphone. Now, here you go. We're measuring the position of the speaker with respect to the microphone. We are using a ruler or a meter stick, which has this resolution. And one more thing that I gotta tell you, the oscilloscope has this ruler here in its screen. Okay, and it has a given resolution here in this ruler. The resolution of this ruler is in reality, 0.2 divisions. So the resolution is going to be 0.2. You use only the first decimal place as for the significance figures, okay? Scale of the scope, assuming it has infinitely precise, okay? And what else did I tell you? Let me show you something else that I didn't tell you. Let's see here. Sound of the scope. You know what? Let's move here. Yeah, okay, here you go. That's the one I want to show you. Okay, here's the scope. I do not know if you can see it, but there is a graduation here in this screen, okay? Let's go further down. You'll be able to see. Okay, here you go. Here are the divisions of your scope, okay? They just make it enlarged, right? In the vertical direction is volts. In the horizontal direction is seconds. Depending on the scale that you use in your scope, and that's what I showed there. You're going to have, for instance, 60 microseconds per square, per division. It varies, depend on the scale that are used in your scope, okay? And the scale of your scope is controlled right here by this knob. This controls the horizontal scale, and this one here controls the vertical scale. You can zoom in and zoom out in this scale to get better or worse measurements, okay? And that's important to know too, because that's exactly what we have in our spreadsheet. Let's take a look at our spreadsheet. I'm going to open here the spreadsheet. Okay, so here you go. Horizontal scale, see that? We can vary the horizontal scale of your scope. In this specific lab experiment, those students use this horizontal scale, 0.2 seconds for every division, but you can adjust to different scales. Okay, here you go. So what you see, if we were to use 0.2 seconds per division, this distance here in the scope would correspond to 2 seconds. Okay, and the distance from peak to peak would be approximately 2 divisions. I would say that the period of this wave that you see here would be 0.4 seconds because it's 2 divisions. 1, 2. 0.4 seconds. Okay. And that's what the students were measuring that. And then he counted the number of divisions. Okay. In that example that I showed to you, it was roughly 2 divisions. It looks like a little bit more than 2 divisions. Yeah, it's a little bit more than 2 divisions. If you take a look here, it looks like it's 2.2 divisions. Okay, 2, 4, 6, 8, 10. 1 full division. That looks like. And here, he determined as being 1.9 divisions. In the next one, he determined 2.9 divisions. And I'm going to show you, number of divisions times the scale is how long it takes for the signal to arrive the microphone. So this is data, this is raw data, and this is a result. Okay? All those three here are data, and this one here is a result because it's multiplying one by the other in seconds. This one here is raw data because the distance between the speaker and the microphone. So those three are raw data. And what are we doing here? We are varying the distance between the speaker and the microphone. This one in this case is 8.7 centimeters. Next one is 15 centimeters, 20 centimeters, 25, 30, 35, and 40 centimeters. And here, okay, raw data, raw data, raw data. Result, result. The speed is obtained by dividing x by t. Okay? And we're going to do better than that. We're not going to just divide. When I do that, let's see, I'm getting, well, we got to get here the unit, right? We're going to do better than that. We're not going to just calculate the speed. What you're going to do, you're going to plot x versus t. Okay? And from that experimental result, you're supposed to get a straight line. Okay? Since I'm plotting x along the y-axis and t along the x-axis, the slope of this graph must be the speed of the sound. Linear, display equation on chart, everything. And then what do we get? I'm getting 0.3682. Why is that I'm getting 0.3682? It's supposed to be 300, right? But I'm getting why is that? Oh, yes, there's a reason for that. That is a reason for that, okay? The students here failed to write this value here in the actual unit. It's not 0.2 seconds per division, okay? It's in reality 0.2 microseconds per division, okay? That's why we're getting this strange result. So we go. If we do this way, you will get the right result. Hopefully your data there is correct and not incorrect like mine. That's for group number 8. Okay, now let's see. Now you are getting the right result. See that? 368 meters per second. Okay, students didn't see there in the scale of the knob of the scale of the oscilloscope that it was milliseconds. Let's see if we can get a zoom view of a oscilloscope. Oscilloscope. See here. Oh, here you go. This one is good. You can take a.
Novo curso de eletrônica digital do Instituto Universal Brasileiro.
Let's skip. Okay, it's coming closer and closer. I'll try to freeze it. Maybe here. Let's see. Here is the knob that controls the horizontal scale. Let me see. This one. Yeah, that looks like this one. That's right. See the scale here, 500 microseconds. Unfortunately, this one is a new one.
YouTubers.
That's it.
Welcome to the session where
Let's take a look at all the oscilloscopes.
how to use the oscilloscope. It's perhaps just
All the oscilloscopes are easier to. All the oscilloscopes. Let's see this one here. Yeah, it looks like. Do you see here we have some knobs right here? Okay, so we have this scale right here. Let's see, the values of V won't go to one sig fig. They stay at whole numbers with 3 sig figs at maximum. Okay, let's see, which group are you? You might be doing something group 2, right? Let's take a look. Group 2. Okay, so you can, let's see, horizontal scale, number of divisions, right? What the horizontal scale here would have infinite numbers of significant digits, okay? But this one, no, this one has just a decimal place, up to the first decimal place. So this one can be, 2 or 1, right? Okay, so if you are combining, 2 significant figures here, right? Then you have to have 2 here as well. Here you have to have 3 decimal places, okay? Okay, here you have 3 decimal places, and here, you should have 2 decimal places, 2 significant figures. Okay, this one would be, this one would be 2 significant figures as well. So it will be 2 significant figures here and at most 3 decimal places. Then the V should have at most 2 significant figures. If I were to write this one properly, right? Format cell number with, we have to do this one now with scientific, with just 1 decimal place. That would be the right way of writing the velocity in scientific format with 1 decimal place. Okay. Okay, so that's one. So that's one of the scales here that you have. That's the type of scale that we have in those old oscilloscopes. Okay. And so go ahead, plot the graph. Okay, plot x versus t is looking at the speed of the sound. If you're getting 0.3 meters per second, must be because the guy failed to write down with the proper scale, the proper horizontal scale, which would be 0.2 milliseconds per division. Okay, so this is the speed of sound, log the slope in table, what table? In the third table. Log the slope in the third table. In the third table. Check the percentage difference. Check the percentage difference. Okay, percentage difference will come here. Don't forget to put the units. And then, do the rest here in terms of CL. Check the percentage difference on the log the slope on the third table. In the third. Let's see. On the third table. Yeah. Check the percentage difference. Work on the units or on the sig figs. Determine the CL. Those are the steps. And let's see how you're all doing. I didn't take attendance yet, right? So let's take attendance. for the lab. Lab attendance today, let's see, 6. 6 was the exam, right? Yeah, 6 was the exam. Exam 3. Exam 3, and now the next one is going to be the 10th. Amy, Han, are you there? Good. Alisa, are you there, Alisa?
I'm here.
Thank you. Next is Ashley Tai. I don't see Ashley here. Next is Sartak. Thank you, Sartak. Mary. Hello, Mary. Looks like Mary is away from her computer. Next one is Raymond. Thank you, Raymond. Next is Basilio Lopez.
I downloaded it, Professor.
Okay, good. Thank you. Yeah, I should ask you, right? Everybody downloaded, right? This let's see here. This would be the 7 download. Huh? I mean, did you download the spreadsheet? Yes, okay, good. Alisa, did you manage to download it?
Yeah, we're done with the lab.
Ah, you're done already. Sartak, did you download the spreadsheet? Good. Mary, is Mary there? Okay, next is gonna be Raymond. Did you download the spreadsheet? Yeah, thank you. Basilio downloaded. Next is Joshua. Are you there?
I'm here, Professor.
Okay, download the spreadsheet.
I completed the lab.
I complete. Okay, good. Zaid downloaded. That's good. And Kartika? Kartika is not answering. Gonna put a little star here. Sydney, did you download the spreadsheet?
Yes, I
Oh.
did.
Are you done too?
Yeah, I'm finishing up the confidence level and then I'll be done.
Okay. Thank you. Next is, let me save that before this thing crashes. Now my spreadsheets are behaving very strangely in my computer. Sumana, did you download the spreadsheet?
Yeah, we downloaded it.
Okay. Kyriakos? Hello, Kyriakos. Did you download the spreadsheet? Yes. Okay, good. Yes. Andy, did you download? Okay. And Alex Hernandez. I don't see Alex Hernandez here. I see. And Alexis Madrigal. Yes, we're finished. Okay. So let's see what you're getting there. So I want to know the slope, okay? Of everybody. I want to make sure what are you getting for the slope, Amy? Hello, Amy, are you there? Let's move on to Alisa. Alisa, what are you getting for the slope?
We're getting 341.98.
Okay, makes sense. Okay, let's go for the next group. Sartak, what are you getting for the slope? $345. Okay, 345.42. That's good. And let's go for the next group. Yeshwan, what are you getting for the slope?
I'm getting 358.27.
58. Okay, good. Next group, Sydney, what you're getting for the slope?
352 meters per second.
Okay, that's good. Group 5 now. Andy, what you're getting for the slope? 347. Okay, so everybody's there in the right ballpark. Okay, and that's Basically, that's what you need to know. Make sure you understand what I explained here. Okay, and position, right? 3 decimal places, resolution of the division, and the scale of the scope. Okay? The scale of the scope, like I mentioned, it has different scales. Let's check the different scales of that I have here in the spreadsheet. Okay, in this case here, group number 2, right? The scale. This scale is 0.5 milliseconds. Do you want us to solve for x? Sine, it says x equal. Yeah, x equal, that's right. X equal the slope times t, right? That's what you do. X is slope times t plus whatever intersect you get from for the regression equation. Make sense, Sartak? In my case, let's see. I want to give you an example. In my case, I don't want to do for group number 2. I want to do for group number 8. In my case, insert, right? Put it here, add trend line, display 368T, right? The way I write, the correct way to write that would be 368T minus 0.058. Okay. If I want to be picky about the units, I write it down 368 meters per second times t minus 0.058 meters. That's how you do it. Okay. An example. Let me erase that. Let me erase that. And any other questions? Karthika, are you there? I have a question. Yeah, go ahead. What's the question?
Yes, I'm here.
Who is that?
Oh, I'm here.
Yeah, what's your name?
Oh, Kartika.
Karthika, okay, good. Okay, thank you. Anybody else? No. No, it's not this one. It's this one here. What am I doing? Karthika is here. And what about Mary? Mary, are you there? Like I would let you know further in this. I'll let you know further in this. Okay. What should be the sig figs of V? Since it is 2 sig figs, yeah, That's right. Let's take a look again, right? Here. In my case, it's asking the significant figure of V, right? So here you go. This V, I'm talking about the significant figure of this V. The slope, you don't need to worry about significant figures, right? Okay, horizontal scale has infinite numbers of significant digits, so you don't have to worry about that. The division, like I said, the division has to be written in terms up to the first decimal place. Okay, at most you're going to get two significant digits. Okay, at most. In my case, in this example here, I'm gonna write down in terms of the significant digit in my example. It's not exactly what you have, but you should have something like that. Okay. Then this one here has infinite number of significant digits because it's the horizontal scale. Okay. If this one has infinite number and this one has 2 significant digits, so the t, which is a function of those 2 measurements, must have 2 significant digits as well. Okay. That's what we have. Here we go. Format cell. I'm going to put in scientific format with 1 decimal place so I can get 2 significant digits. 2 significant digits here, 2 significant digits here, right? Everything. My x is supposed to have 3 decimal places because I'm measuring the distance or position. 1, 2, 3. This one has 2 decimal places, has 2 significant digits, and this one has 2 significant digits. how many secant digits do we have to put here? 1 divided by the other. Okay? Okay, Andy? This one has 3 secant digits, this one has 2. How many secant digits do we put here? Right? Here, 3 and 2. How many do we put here? And so on. Okay? And then how do we format that? You have to format it properly, right? You cannot write 3 in the regular number. You have to write it in scientific format. You have to write in scientific format, but you have to put a decimal place there. Now I have it displayed in the proper number of secant digits. In this specific case, he's getting at 230 meters per second for the speed of the sound. And I know why. Okay, there's a reason for that, okay? But this one doesn't count. What counts for the speed of the sound is this slope. Okay? This is just one lonely measurement. Whereas this one here is not a one lonely measurement, it's 7 different measurements that you take the average and you end up with the right. Do I round down in Excel? Well, Excel already does the rounding down for you. You don't have to worry about that. See that? This one here already put that in the decimal places, and Excel does that automatically for you. Now let me undo everything that I did. This one, okay, and now we have it in the way I want. I'm gonna put here, red. Any more questions? 142, we're almost over. So review the video, right? Review the figures, review the notes. I'm gonna ask questions from this lab and the other labs as well. Okay? You must know the story, how it goes. Let's see if they have one of those experiments of sound here. Speed of the sound experiment. Oh yeah, see that? Similar to what we do there at LA Harbor. Let me see here. Look at it. Look at sound resonance tube. Let's see. Yeah, he has a scope. He has a function generator. Let's take a look at this one. It doesn't look like it's exactly ours because he's using a resonance tube. I didn't measure the speed of sound. I don't like this. Yeah, this one is a long distance. See that? Not about this one. Okay, that's a resonance column. Speed of sound, level of physics, core practical. Experiment of sound. The speed of sound with a smartphone. Let's take a look at this one. Let's see if he did exactly the way he used. Oh, sound experience set laboratory sound wave. I don't see the speed. Okay, let's take a look at this one. Oh, skip. Okay.
What we have here is a piece of apparatus that will.
No, see the speaker, right? The speaker is connected to the function generator here. It looks like it's connected to the function, but I don't see the microphone. Let's see how he did this experiment. Might be a different way of measuring the speed of sound.
Calculate the speed of sound. The apparatus consists of a perspex tube, closed at one end, open at this end. At the open end, I have a loudspeaker so I can pump sound into it. The loudspeaker is driven by this function generator with an adjustable frequency. We're going to start with a frequency of 625 hertz. Inside the tube, you'll see there's a little microphone on a stick.
Oh yeah, here you go. That's how I do it. Yeah, there's a microphone here at the end of the stick. See, that's how he changes the position of the microphone instead of using that bench that I mentioned to you. What's the advantage of this setup? It's very important. You know, the advantage of the setup is that the sound becomes trapped inside this tube, and you can move away from the source for long distances. Okay, when we do the experiment the way that I mentioned to you, let's go back here to this one. You know, there is no guiding here for the sound. There is no tube here of the sound to concentrate the sound inside a small region. So the sound propagates everywhere in every possible direction, and you may lose intensity of the sound here in the speaker. So if you do the experiment in that way, you can concentrate most of the sound in this volume, right? To measure the sound with the microphone.
Is marked by this flap of cardboard. The idea is we're going to send the sound through here, but we've chosen the frequency so that we get resonance. So in other words, we'll get a regular set of nodes and antinodes
Okay.
along here because it'll be a standing wave. And we're going to measure the distance between nodes because from that information we can work out the wavelength. We have wavelength, you know the frequency, and you should be able to calculate the speed of sound.
Yeah, he's indeed doing the experiment in a different way, okay? From what he's saying here, he's using the resonance frequency, but you can also do the time of flight experiment with this tube. That's how I used to do there in the LA Harbor. We put the microphone in there. Well, let's keep on watching that.
Well, let's start the experiment. Oh, you'll notice here that I have an oscilloscope. The oscilloscope is connected to the microphone, so you'll be able to see the output of the microphone. Wherever you see a high amplitude output, you'll know that you're at an antinode, and when you see low amplitude output, you know you're at a node. So let's start moving the microphone
away. Let's see, it's increasing. Okay, what's happening here? He's got the oh, that's nice. I like this experiment. I should do that. That's the node. That's the node. Okay, that's another way of doing the experiment. Let me just momentarily pause here. What's happening here? We have a sound wave with maximum amplitude. We have a standing wave here. That's a sound wave that is a standing wave. At this point, you have maximum amplitude, and right here where the microphone is, you have a node. That's a different way of doing the experiment, okay? And by locating those nodes, you can find out what the speed of the sound, because by locating those nodes, you can find out what's the wavelengths, okay? From the wavelengths, you have the frequency. Frequency times wavelength is going to be the speed. And again, and he's using a sine wave here, okay? He's using a sine wave here. He's not using a square wave like I do in the experiment. So two different ways of doing the experiment. The equipment is the same, but the procedure is different. I think this one is interesting. More interesting. So he's looking for the destructive interference, for the point of destructive interference. The node. This end is open, but this end here is closed, okay? This end here is closed. You must have a closed end to form a resonant cavity, to form a cavity that the wave resonates. So now he's gonna mark the position, right? You go. Yeah, he's marking the position of the microphone.
First node. So let's find another node.
Another node, let's find another. Oh, see that? Right now, he is a point of almost constructive interference. Can you picture here? Maximum amplitude here, zero amplitude here. Now you have a maximum amplitude around here, right? Yeah, and now he's gonna get to the position of destructive interference. That's what the oscilloscope is registering. He is registering the position of the intensity of the sound at this point, right?
So that's it.
And he mark it again. Here you go. Another node.
It's a good measure. We'll find position 2.
Let's get next position of node. The next node position. He's coming. He's coming. See that? It's amazing that we can do different experiments, different procedures with the same equipment. Okay, here you go. Node.
I know you want more, so I'm going to find one more node.
Let's see if we can find another node here. The node should be very close to the end of the tube. It's a little bit further away, so it doesn't look like it has a. We are supposed to get a node there at the very end of the tube.
Turn that annoying sound off.
So it looks like that this end here is not completely closed. That's what it looks like. Otherwise, you're supposed to get a node right here at the end, okay?
You may remember that the spacing between nodes in this situation is a half a wavelength. So I'm going to measure the 2 nodes, and that will give me 1 wavelength.
Every 2 nodes you have a full wavelength.
Right? I make that 55.5 centimeters.
Okay.
Between that's the wavelength.
From here to
So
here, 55.5.
hertz, wavelength 55.5 centimeters. Now, don't forget to convert to SI units. Now, being scientists, we don't rely on one measurement. We're going to repeat this measurement with a different frequency.
Oh, here you go. It's going to do a different frequency now.
Okay, I'm back again, but this time we're going to be using 885 hertz.
885. The other one was 55.5 centimeters, right? By the way, I don't remember the frequency of the other one. Here you go. Okay. Let's go back to let's see what was the frequency, the previous frequency. Node. Frequency.
And we're going to measure the distance between.
Let's see. Did he say what the frequency? Oh, 825. That was the frequency.
625.
Oh,
hertz.
625.
Inside the tube, you'll see there's a little microphone on the stick.
And now you can multiply one by the other.
Like a cardboard.
And you should be able.
The idea is we've.
Oh, yeah. So
through here.
625 hertz times 0.55, right? If you were 0.5, would be just 310, but it's a little bit more than that. 625 times 0.555, 346. And then he repeated the experiment for a different frequency, right? He got the nodes at different place. And here you go, he's doing the second part of the experiment. The nodes are closer. Let's see what's the wavelength that he's getting. 39 centimeters.
SI units.
Okay. The second frequency was higher, right? 800 and whatever. Consequently, the wavelengths must be shorter. And now he's going to do the calculation. Here you go, the data. This time, this is the speed of the sound. This time, this is the speed of the sound. That's right. The final exam is 8 a.m. to 10 a.m. Just like it's displayed in the schedule of classes, okay? So 2 different ways of doing the same experiment. And 154 right now. Let me write down again here. I don't want anybody to lose the final exam, right? If you miss the final exam, then it's an automatic F. So don't miss the final exam. Here you go. Final exam is 14th. No, it's the 13th. It's July 13th. July 13th from 8 a.m. to 10 a.m. Okay. Just like also it's in the syllabus right here. Partial exams are from 12 noon to 2 p.m. The final exam is from 8 a.m. to 10 a.m. Okay. I'm gonna put a different line here. So there is no confusion about the time. Any questions, any further questions about that? What lab will be test? Everyone that we do. Lab 1, 2, 3, 4, 5, 6, and 7. Okay. Everyone, you are gonna have the notes for all those labs, right? The notes are all written down. You'll be able also to check the recordings. Let me